family. Today marks the fourth death anniversary of Professor K. Gopalakrishnan Nair. On this solemn occasion, we remember and honor a visionary academician, an inspiring teacher, and a pioneer who played a transformative role in shaping electronics education and nurturing scientific culture at the Cochin University of Science and Technology. To begin this tribute, may I request everyone to kindly rise as we observe a moment of silence in his loving memory. Thank you. Please be seated. We shall now invite our esteemed dignitaries to the dais. I respectfully invite Professor Arun A.U., Dr. Duvvuru Seshagiri, Professor K. Babu Joseph, Professor K. Shivaprasad, Sri Rajan Tuvara, Dr. M. Gopalakrishna Pillai, Dr. Deepti Das Krishna to kindly take their seats on the dais. Thank you all. To formally welcome the gathering and set the tone for today's program, I now invite Dr. Deepti Das Krishna, Head of the Department, Electronics, CUSAT, to deliver the welcome address. Over to you, ma'am.
Thank you, Vishnumaya. So, respected dignitaries on the dais, distinguished speaker, Dr. Duvvuru Seshagiri, members of the family of Professor K.G.N., faculty, my faculty colleagues, retired faculty members, staff, and my dear students, and also invited guests, a very good morning to one and all. Now, it is said that fragrance lingers even after the flower has wilted or disappeared. And even more enduring is the fruits which are born out of the seeds which are sown and nourished properly. So Professor K.G. Nair was a noble presence whose influence spread far and wide, whose legacy transcends space and time, and generations after him continue to enjoy and cherish the fruits of his vision, dedication, and tireless labor. So today, as we observe his fourth death anniversary, we gather not to merely remember him, but to honor and celebrate his legacy as a great teacher, proponent of science and society, institution builder, and a visionary. So he had been instrumental in establishing key institutions like the Children Science and Society, CSIS, STIC, and most importantly, this very Department of Electronics, which recently marked its 50th anniversary. So as the head of the department for 15 long distinguished years, he had laid foundation for its growth, excellence, and its reputation. So this memorial lecture stands as a humble tribute to his remarkable life and legacy. And it is both my privilege and honor to deliver the welcome address on this occasion. So we are honored to have with us today our distinguished speaker, Dr. Seshagiri, outstanding scientist and director of NPOL. An eminent scientist and leader in defense research, Dr. Seshagiri has contributed significantly to the advancement of airborne defense systems, enabling our country to develop them indigenously. So we are grateful to him for graciously accepting our invitation to deliver the memorial lecture in the area of sensors for airborne warfare. Welcome you, sir. I extend my respectful welcome to Professor Arun A.U., Registrar, Cochin University, for presiding over this function, sir. We welcome you, sir. I also warmly welcome the former Vice Chancellor of Cochin University, Professor K. Babu Joseph, the former Vice Chancellor of Kerala Technical University, Professor K. Shivaprasad, eminent writer, Dr. Sri Rajan Tuvara, representing K.G.Nair sir's family. He is joining us very soon. He'll be here with us. So I welcome him as well. So they are here to offer tributes to Professor K.G.N. And I welcome all of you, sir. So there are family members of Professor KGN here who are joined. So I welcome them also. And there are also those who have joined online through our Zoom link, particularly his sons from USA, without whose support this program would not have been possible. So I extend my warm welcome to all of them. And last but not the least, we have Dr. M. Gopalakrishnan Pillai, the director of STIC, without whose initiative and support this program would not have been possible. And my heartfelt welcome to all the invited guests who have joined here, and to the current faculty members as well as the retired faculty members who have come here, research scholars, students, all of them who have joined together to honor Professor KGN and his contributions. So now, as we begin this solemn and meaningful program, let us not only remember Professor Nair, but also renew our commitment to ideals he embodied. That is excellence in scholarship, dedication in service, and integrity in thought and action. So once again, I welcome you all and thank you for being part of this significant occasion. Thank you.
Thank you, ma'am, for the warm and gracious welcome. It is now my honor to invite Professor Arun Ayu, Registrar, CUSAT, to deliver the presidential address.
Chief guest of the day, Dr. University, Dr. Deepthi Das Krishna, Head Department of Electronics, CUSAT, Sri Rajan Tuvara, Writer, Dr. M. Gopalakrishnan Pillai, Director, STIC, retired faculties, current faculties, students, and dear participants, and my dear friends. First of all, I congratulate the department as well as STIC for organizing this memorial lecture of Professor K.G.Nair. I happen to know Professor K.G.Nair while I was a student of this university from 1993 onwards, because at that time only few departments were in Kochi University Science Center, especially in the main campus. One will be Department of Electronics. So majority of the students in Department of Electronics were staying in Sarovar hostel. So I was also an inmate of Sarovar hostel. So I used to have many friends in electronics department. Through that way, I used to have some familiarity with Professor K.G.Nair. So from that time onwards, we happen to know that the eminence that he is having, I think, when popularizing the science to the common man, what are the activity he's doing? In connection with that thing, I think we have many discussion with Professor K.G.Nair, and I ask all of you know, he is the main pillar regarding the establishment of science in society as well as STIC in Kochi University of Science and Technology. After the retirement also, he is used to write for the common man as well as the students to know what are the science to the common man. Normally, science is mainly focusing on the elevated class or the educated class. As far as his contribution is concerned, he's normally worked hard to bring the common science or basic science to the common man as well as the students. So in this area, he has done a lot of work. In that area, I think still we are remembering Professor K.G.Nair, his contribution to the science, especially popularizing the science. In connection with that thing, we are celebrating the Professor K.G.Nair Memorial Lecturer. I think his colleagues are present here. I think former Vice Chancellor, Professor Babu Joseph is there. I think he's a good association with Professor K.G.Nair. I think he will explain what are the things I think normally he has done his during tenure. So once again, I congratulate the department for organizing Professor K.G.Nair Memorial Lecturer this year. Thanking you. Thank you.
Thank you, sir. We now move to a heartfelt segment of today's program, the tribute address, where we remember and celebrate the life and legacy of Professor K.G. Nair through the words of those who knew him closely. First, may I respectfully invite Professor K. Babu Joseph, former Vice Chancellor of CUSAT, to share his tribute and cherished memories.
Professor Arun, President of the meeting. Dr. Duvvuru Seshagiri, the Memorial Lecturer and Director of NPOL, other distinguished guests on the dais and off the dais, my former colleagues and friends. I'll be doing injustice to the revered memory of my longtime friend, the late K.G.Nair, if I speak in English. So with apologies to at least to Dr. Duvvuru, let me switch over to Malayalam because it was a favorite language of Professor K.G.Nair. I'll be remembering some of the episodes in which I too had a part, at least as a spectator. സുഹൃത്തുക്കളെ, കെ.ജി. നായർ ആകുന്നതിന് മുമ്പ് വെളിയനാട് ഗോപാലകൃഷ്ണൻ നായരായിരുന്നു. ഞാൻ അദ്ദേഹത്തെ വെളിയനാട് ഗോപാലകൃഷ്ണൻ നായർ ആയിട്ടാണ് അറിയുന്നത്. അദ്ദേഹം ആവശ്യപ്പെട്ടതനുസരിച്ച് പിന്നീട് ഞങ്ങൾ നായർ എന്നുള്ള വാല് മുറിച്ച് കളഞ്ഞു. ഡോക്ടർ വെളിയനാട് ഗോപാലകൃഷ്ണൻ, ഡോക്ടറും വേണ്ട, വെളിയനാട് ഗോപാലകൃഷ്ണൻ എന്ന പേരിൽ അറിയപ്പെടാനാണ് അദ്ദേഹം ആഗ്രഹിച്ചത്. അദ്ദേഹത്തിൻ്റെ ജീവിതം തന്നെ അതിന് സാക്ഷ്യമാണ്. അദ്ദേഹത്തെ ഞാൻ പരിചയപ്പെടുമ്പോൾ ഞാനൊരു റിസർച്ച് സ്കോളറായിരുന്നു, സീനിയർ റിസർച്ച് സ്കോളർ ഫിസിക്സ് ഡിപ്പാർട്ട്മെൻറ്റിൽ. അന്ന് ആലുവയിൽ UC കോളേജിലായിരുന്നു ഫിസിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ്. അവിടെ നിന്ന് ഇവിടെ വന്നു. അപ്പോൾ ഗോപാലകൃഷ്ണൻ സാറെന്നാണ് ഞങ്ങൾ വിളിച്ചിരുന്നത്. അദ്ദേഹം ലെക്ചറായിരുന്നു. അദ്ദേഹം പോലെ ഡോക്ടർ CP മേനോൻ സീനിയറായിരുന്നു, റീഡറായിട്ട് ഇവിടെ ഉണ്ടായിരുന്നു. അദ്ദേഹത്തിന് അതുപോലെ തന്നെ ഡോക്ടർ ജോയ് ജോർജ്, ഇത്രയും പേരാണ് ഫിസിക്സ് ഡിപ്പാർട്ട്മെൻറ്റിൽ ഫാക്കൽറ്റി ആയിട്ട്. റിസർച്ച് സ്കോളേഴ്സ് പലരും ഉണ്ടായിരുന്നു. എനിക്ക് തോന്നുന്നു ഞാനായിരുന്നു സീനിയർ മോസ്റ്റ്. ഏതായാലും റിസർച്ച് സ്കോളർ അല്ലെങ്കിൽ വിദ്യാർത്ഥി അധ്യാപകൻ എന്നുള്ള ആ വ്യത്യാസമൊന്നും കൂടാതെ എല്ലാവരോടും ഒരുപോലെ പെരുമാറിയിരുന്നു അന്നത്തെ ഫാക്കൽറ്റി. ഞാൻ പറയാൻ വിട്ടുപോയ ഒരാളുടെ ഉണ്ട്, ഡോക്ടർ G. അരുൾദാസ്. അദ്ദേഹം വർഷങ്ങൾക്ക് മുമ്പ് മരിച്ചുപോയി. ഇവരെല്ലാം ഞങ്ങളെല്ലാം വളരെ അടുത്ത സുഹൃത്തുക്കളെ പോലെയാണ് പെരുമാറിയിരുന്നത്. വിദ്യാർത്ഥികളിൽ എന്നോടൊപ്പം ഉണ്ടായിരുന്ന ഡോക്ടർ CP ഗിരിജാവല്ലഭൻ തൊട്ട് കുറേ പേരുണ്ടായിരുന്നു. അവരാരും തന്നെ ഇവിടെ കാണുന്നില്ല. ചിലരൊക്കെ മരിച്ചുപോയി, ചിലരിപ്പോഴും ഉണ്ട്. അദ്ദേഹത്തിൻ്റെ സംഭാവനകളെക്കുറിച്ച് പറയാനാണെങ്കിൽ മണിക്കൂറുകൾ വേണ്ടി വരും. എനിക്കറിയാവുന്ന കാര്യങ്ങൾ തന്നെ ഒത്തിരി പറയാനുണ്ട്. പക്ഷേ എനിക്ക് 7 മിനിറ്റാണ് ഇവിടെ പറഞ്ഞിരിക്കുന്നത്. അതുകൊണ്ട് വളരെ ചുരുക്കി പറയാം. ഇവിടെ പ്രൊഫസർ അരുൺ ഇതിനകം സൂചിപ്പിച്ച കാര്യം പോപ്പുലർ സയൻസിന് അദ്ദേഹത്തിൻ്റെ സംഭാവനകളെക്കുറിച്ചാണ്. അത് 1960 അദ്ദേഹത്തിൻ്റെ ഒരു പുസ്തകം ശാസ്ത്രവീഥിയിലെ നാഴികക്കല്ലുകൾ അത് പ്രസിദ്ധീകരിച്ചു. അതിൻ്റെ പേരിലാണ് അദ്ദേഹം ഏറ്റവും കൂടുതൽ അറിയപ്പെട്ടിരുന്ന ആദ്യകാലങ്ങളിൽ. ഞാനും അതിൻ്റെ ഏതാനും ഭാഗങ്ങളെങ്കിലും വായിച്ചിട്ടുണ്ടാവണം. കൂടാതെ അദ്ദേഹം മാസികകളിലും വീക്കിലികളിലുമൊക്കെ ലേഖനങ്ങൾ എഴുതുമായിരുന്നു, ശാസ്ത്രലേഖനങ്ങൾ. അന്നൊരു പുതിയ മേഖലയാണ് മലയാളത്തിൽ ശാസ്ത്രലേഖനങ്ങൾ. അതിന് പ്രോത്സാഹിപ്പിക്കാനായി എൻ വി കൃഷ്ണവാര്യർ, പി ടി ഭാസ്കര പണിക്കർ തുടങ്ങിയ മഹാരഥന്മാരുണ്ടായിരുന്നു. മലയാളത്തിൽ പ്രസിദ്ധീകരണങ്ങൾ, ശാസ്ത്ര പ്രസിദ്ധീകരണങ്ങൾ ഇറക്കുന്നതിന് വേണ്ടി കേരള ഭാഷാ ഇൻസ്റ്റിറ്റ്യൂട്ട് സ്ഥാപിച്ചു ഇതിനിടയിൽ. അപ്പോൾ അതിൽ പുസ്തകങ്ങൾ എഡിറ്റ് ചെയ്യാനൊക്കെ അറിയാവുന്ന ആളുകൾ അപ്പോയിൻ്റ് ചെയ്യാനുള്ള സമയമില്ല, ആളുകൾ തന്നെ കുറവാണ് സ്റ്റേറ്റിൽ. അതുകൊണ്ട് പലരെയും ഡെപ്യൂട്ടേഷൻ വിളിക്കാൻ അവർ തീരുമാനിച്ചു. കൃഷ്ണമാർ ആയിരുന്നു ഡയറക്ടർ. ഫിസിക്സിൻ്റെ എഡിറ്ററും ഗസ്റ്റ് എഡിറ്റർ എന്നാണ് പേര് ആയിട്ട് ഗോപാലകൃഷ്ണൻ സാറ് ആണ് പോയത്. ഞങ്ങൾ ഗോപാലകൃഷ്ണൻ സാറിനെ വിളിച്ചിട്ടുള്ളൂ, K.G. നായർന്ന് ഒരിക്കലും വിളിച്ചിട്ടില്ല, K.G. നായർ സാറേന്നും വിളിച്ചിട്ടില്ല. ഇപ്പോഴും ആ വെളിയനാടെന്ന് ചിലരൊക്കെ വിളിക്കുമായിരുന്നു, വെളിയനാട്. അദ്ദേഹം അവിടെ പോയി. അദ്ദേഹം ചെയ്തത് അദ്ദേഹത്തിൻ്റെ സഹപ്രവർത്തകരായ ഞങ്ങളീ കുറേ പേരെ മോട്ടിവേറ്റ് ചെയ്യണം. നിങ്ങൾ മലയാളത്തിൽ എഴുതുക, അല്ലാതെ ഇംഗ്ലീഷിൽ വല്ലതൊക്കെ എഴുതി പേപ്പർ പബ്ലിഷ് ചെയ്തിട്ട് എന്താ കാര്യം? സാധാരണക്കാർക്ക് വേണ്ടി എന്തെങ്കിലുമൊക്കെ ചെയ്യണം. ആ കാര്യത്തിൽ അദ്ദേഹം വളരെ നിഷ്കർഷ പാലിച്ചിരുന്നു. വെറും സംസാരം മാത്രമല്ല, പ്രവൃത്തിയിലും സാധാരണക്കാരോട് ഐഡൻറ്റിഫൈ ചെയ്യാനായിട്ട് അദ്ദേഹം ശ്രദ്ധിച്ചിരുന്നു. അദ്ദേഹം വളരെ പ്രയാസങ്ങൾ സഹിച്ചാണ് അദ്ദേഹത്തിൻ്റെ വിദ്യാഭ്യാസം നടത്തിയത്. BSc കഴിഞ്ഞ് ഒരു വർഷം UC കോളേജിൽ ഡെമോൺസ്ട്രേറ്ററായിരുന്നു. അത് കഴിഞ്ഞ് MScക്ക് യൂണിവേഴ്സിറ്റി കോളേജിൽ പോയി. അവിടെ പഠിച്ചതിന് ശേഷം റിസർച്ചിന് ചേർന്നു. അന്ന് റിസർച്ച് സ്കോളർഷിപ്പ് എന്ന് പറഞ്ഞാൽ ഒരു പിറ്റൻസ് മാത്രമേ ഉള്ളൂ. അത് എത്രയാണെന്ന് തന്നെ പറയാൻ വയ്യ. ഞാൻ സ്കോളർഷിപ്പ് എനിക്ക് കിട്ടിയത് 250 രൂപയാണ് മാസം. അപ്പോൾ അതിലും കുറവായിരുന്നു എൻ്റെ മുൻഗാമികൾക്ക് കിട്ടിയിരുന്നത്. അദ്ദേഹം ഡോക്ടർ ഹരിഹർ എന്ന പ്രൊഫസറുടെ കീഴിലാണ് റിസർച്ച് ചെയ്തത്. യൂണിവേഴ്സിറ്റി കോളേജിലെ പ്രൊഫസറായിരുന്നു. അപ്പോൾ ദൈനംദിന ജീവിതത്തിന് വരും ബുദ്ധിമുട്ടിന് ആ കാലത്ത് സാറ് അവിടെ ഒരു ട്യൂട്ടോറിയൽ കോളേജിൽ പോയി ക്ലാസ് എടുത്തിരുന്നു. അപ്പോൾ വെളിയനാട് ഗോപാലകൃഷ്ണൻ എന്നുള്ള അധ്യാപകന അന്ന് തൊട്ടേ തിരുവനന്തപുരം തൊട്ട് അദ്ദേഹത്തിൻ്റെ പ്രശസ്തി ആരംഭിക്കുന്നു. തിരുവനന്തപുരത്ത് അധ്യാപകൻ എന്നുള്ള രീതിയിലാണ് അദ്ദേഹത്തെ പറ്റി കേട്ടിട്ടുള്ളത് തന്നെ. ഏതായാലും അവിടെ നിന്ന് ഇങ്ങോട്ട് പോന്നു. ഇവിടെ വന്ന് ദീർഘമായ ഒരു അക്കാഡമിക് ജീവിതമാണ്. അതിൻ്റെ ഇടയിൽ സെനറ്റ് മെമ്പർ, സിൻഡിക്കേറ്റ് മെമ്പർ, അങ്ങനെ പല തസ്തികകളിൽ അദ്ദേഹം വഹിച്ചു. കൂടാതെ അദ്ദേഹത്തിൻ്റെ സാമർഥ്യം എന്ന് പറഞ്ഞാൽ വെറും അക്കാഡമിക് സാമർഥ്യം മാത്രമല്ല. ഒരു ഡിപ്പാർട്ട്മെൻറ്റ്, ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ് അത് തുടങ്ങിയപ്പോൾ വേറൊരാളായിരുന്നു പ്രൊഫസറെങ്കിലും താമസിയാതെ ഗോപാലകൃഷ്ണൻ സാറിനെ അങ്ങോട്ട് മാറ്റി. അദ്ദേഹം ആ ഡിപ്പാർട്ട്മെൻറ്റ് ബിൽഡപ്പ് ചെയ്തു. അതിൻ്റെ ഇടയിൽ ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റിൽ നിന്ന് വിരിഞ്ഞതാണ് കമ്പ്യൂട്ടർ സയൻസ്, കമ്പ്യൂട്ടർ ആപ്ലിക്കേഷൻസ് ഡിപ്പാർട്ട്മെൻറ്റ്. അതിൻ്റെയും സൂത്രധാരൻ K.G. നായർ സാറായിരുന്നു. ഇങ്ങനെ ഡിപ്പാർട്ട്മെൻറ്റുകൾ, ഫിസിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ് വളരെ പ്രശസ്തമായിട്ട് മൈക്രോവേവ് റിസർച്ച് ആൻറ്റന്ന എന്ന വിഷയത്തെക്കുറിച്ച് ലാബുകളും റിസർച്ചും ഒക്കെ അദ്ദേഹം ഓർഗനൈസ് ചെയ്തു. അദ്ദേഹത്തിൻ്റെ പൂർവ്വ വിദ്യാർത്ഥികൾ ചിലരെങ്കിലും ഇവിടെ ഉണ്ടെന്ന് തോന്നുന്നു. അന്ന് അവിടെ റിസർച്ച് ചെയ്ത് PhD എടുത്തവർ. ഏതായാലും അദ്ദേഹം വന്നിവിടെ നല്ലതുപോലെ പ്രവർത്തിച്ചു. ഗവേഷണം, അതുപോലെ കോഴ്സുകൾ ഒക്കെ ഓർഗനൈസ് ചെയ്തു. ഇതുകൂടാതെ അദ്ദേഹത്തിൻ്റെ ഓർഗനൈസേഷൻ സ്കില്ലിന് ഉദാഹരണമാണ് 1977 ഇന്ത്യൻ സയൻസ് കോൺഗ്രസ് ഇവിടെ കൊച്ചി സർവകലാശാലയിൽ ഹോസ്റ്റ് ചെയ്തു. അപ്പോൾ അതിൻ്റെ ജനറൽ ഓർഗനൈസറായിട്ട്, കോർഡിനേറ്ററായിട്ട് വൈസ് ചാൻസലർ നിയമിച്ചത് പൈലി സാറായിരുന്നു വൈസ് ചാൻസലർ. അദ്ദേഹം K.G. Nair സാറിനെ നിയമിച്ചു. അദ്ദേഹത്തിൻ്റെ ശ്രമഫലമായി വളരെ സുത്യർഹമായ രീതിയിൽ സയൻസ് കോൺഗ്രസ്, എനിക്ക് തോന്നുന്നത് 7 ദിവസം മറ്റാണ് നീണ്ടു നിന്നത്, ഇവിടെ നടന്നു. അതിൽ ഞാനും ഒരു ഇൻവൈറ്റഡ് സ്പീക്കറായിരുന്നു ചെറിയ തോതിൽ. അതിൻ്റെ തീം സയൻസ് ഇൻ സൊസൈറ്റി എന്നായിരുന്നു. ഞാൻ ഇൻവൈറ്റഡ് സ്പീക്കർ ആകാൻ കാരണം ഗോപാലകൃഷ്ണൻ സാറാണ്. അത് അല്ലാതെ എൻ്റെ യാതൊരു മെറിറ്റ് കൊണ്ടും അല്ല എനിക്ക് ആ ഇൻവിറ്റേഷൻ കിട്ടിയത്. പ്രൊഫസർ യശ്പാൽ എന്ന അന്നത്തെ UGC ചെയർമാനായിരുന്നു ഇതിൻ്റെ ഓവറോൾ ഡയറക്ടർ. അപ്പോൾ ഇതാണ് ആ ഒരു വശം. ഓർഗനൈസർ എന്നുള്ള തരത്തിൽ ബിൽഡർ ഡിപ്പാർട്ട്മെൻറ്റുകൾ 2 കുറഞ്ഞ പക്ഷം ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റെങ്കിലും അദ്ദേഹത്തിൻ്റെ സംഭാവനയാണെന്ന് ഉറപ്പിച്ച് പറയാൻ സാധിക്കും. പിന്നീട് അദ്ദേഹത്തിൻ്റെ എഴുത്ത് ഈ പല പല കാര്യങ്ങളിൽ വ്യാപൃതനാകുമ്പോഴും അദ്ദേഹത്തിൻ്റെ താല്പര്യം കുട്ടികളുടെ ഇടയിൽ ശാസ്ത്രബോധം വളർത്താനായിട്ടുള്ള എന്തെങ്കിലും ചെയ്യണം. എപ്പോഴും പറയുമായിരുന്നു അതിനെപ്പറ്റി. അദ്ദേഹത്തിൻ്റെ ബ്രെയിൻ ചൈൽഡാണ് സെൻറ്റർ ഫോർ സയൻസ് ഇൻ സൊസൈറ്റി. അത് ഇപ്പോൾ വളരെ ഡെവലപ്പ് ചെയ്തു. അതുകൂടാതെ സോഫിസ്റ്റിക്കേറ്റഡ് ഇൻസ്ട്രുമെൻറ്റ്സ് ലാബ് സെൻറ്റർ, അങ്ങനെ വേറൊരു സ്ഥാപനം അദ്ദേഹം സ്ഥാപിച്ചു. ഇങ്ങനെ ഇതെല്ലാം ബഹുമുഖ പ്രതിഭ എന്നുള്ള രീതിയിൽ അദ്ദേഹത്തിൻ്റെ ക്രെഡിറ്റിൽ നിൽക്കുന്നു. ഇത് അദ്ദേഹത്തിന് വാസ്തവത്തിൽ ഒരു അവാർഡ് കൊടുക്കേണ്ടതാണ്. പക്ഷേ അദ്ദേഹം ചെയ്തത് എന്താണെന്ന് വെച്ചാൽ ഇതുപോലെയുള്ള പല തുറകളിൽ സേവനം നടത്തി ഡിസ്റ്റിങ്വിഷ് ചെയ്യുന്ന ഒരു ബെസ്റ്റ് അക്കാഡമിഷ്യൻ ഇന്ത്യയിൽ കണ്ടുപിടിക്കണം. അയാൾക്ക് ഒരു അവാർഡ് കൊടുക്കണം. ഇപ്പോൾ പൈലി സാറ് അതിനുവേണ്ടി ഒരു തുക യൂണിവേഴ്സിറ്റി ഏൽപ്പിച്ചു. അതിൻ്റെ പലിശ കൊണ്ട് എല്ലാ വർഷവും ബെസ്റ്റ് അക്കാഡമിഷ്യൻ ഓഫ് ഇന്ത്യ എന്ന ഒരു വിഭാഗത്തിൽ കൊച്ചിൻ യൂണിവേഴ്സിറ്റി ഒരു അവാർഡ്, ഒരു പ്രൈസ് കൊടുക്കുന്നു. പൈലി പ്രൈസ് എന്നാണ് ഞാൻ പറയുന്നത്. ഏതായാലും അത് അന്നത്തെ നിരക്കിന് അത് 1 ലക്ഷം രൂപയോ മറ്റായിരുന്നു ആദ്യം. അത് 2 ലക്ഷമാണ്. ഏതായാലും പിന്നെ പലിശ നിരക്കുകൾ കുറയുകയോ ഒക്കെ കാരണം ഈ 2 വർഷത്തിൽ ഒരിക്കൽ ആ പ്രൈസ് കൊടുക്കാൻ തീരുമാനിച്ചു. ഇത് പ്രൈസ് കൊടുക്കുന്ന വെറും ആർബിട്രറി ആയിട്ടല്ല, ഒരു ഓൾ ഇന്ത്യ കമ്മിറ്റി ഉണ്ട്. ആ കമ്മിറ്റി തിരഞ്ഞെടുക്കുന്ന ആളാണ് പ്രൈസിന് അർഹൻ. ഇത് ഈ ആശയം പൈലി സാറിനോട് പറഞ്ഞത് ഗോപാലകൃഷ്ണൻ സാറാണ്. സാറിൻ്റെ ഓർമ്മ ഇവിടെ നിലനിൽക്കണമെങ്കിൽ എന്തെങ്കിലും ഒരു കാര്യമായിട്ടൊരു കോൺട്രിബ്യൂഷൻ വേണം. അത് ഇതിൻ്റെ വ്യവസ്ഥകളും എല്ലാം ആവിഷ്കരിച്ചത് ഗോപാലകൃഷ്ണൻ സാറാണ്. സാറ് ഇവിടെ നിന്ന് റിട്ടയർ ചെയ്യുന്നവരെ അതിൻ്റെ നടത്തിപ്പ്, അതിന് ശേഷവും ഈ കമ്മിറ്റിയുടെയൊക്കെ പ്രവർത്തനങ്ങളിൽ ഭാഗഭാക്കായിട്ടുണ്ട്. അങ്ങനെ ബഹുമുഖമായ പ്രതിഭയാണ് നമ്മൾ സ്മരിക്കുന്ന ഗോപാലകൃഷ്ണൻ സാറ്. അദ്ദേഹത്തിൻ്റെ സൃഷ്ടികളിൽ ഞാനൊരു പുസ്തകത്തെക്കുറിച്ച് പറഞ്ഞു, ധാരാളം ലേഖനങ്ങൾ എഴുതി. അദ്ദേഹം ഒരു കവിയും കൂടിയായിരുന്നു. അദ്ദേഹത്തിൻ്റെ ഒരു കവിതയുടെ ടൈറ്റിൽ E=MC². E=MC² എന്നുള്ള കവിത, അത് കൗമുദി വാരിക ഉണ്ടായിരുന്നു, അതിനകത്താണ് വന്നതെന്നാണ് എൻ്റെ ഓർമ്മ. ഈ കവിതയൊക്കെ അദ്ദേഹത്തെ കണ്ടുമുട്ടുന്നതിന് മുമ്പ് വായിച്ചിട്ടുണ്ട്. ഇവിടെ വന്നപ്പോൾ ഞാൻ വിചാരിച്ചതിനും വലിയൊരു മനുഷ്യനെയാണ് കണ്ടത്. അദ്ദേഹത്തിൻ്റെ ഓർമ്മ ഒരിക്കലും മാഞ്ഞു പോവില്ല. അദ്ദേഹത്തോട് ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ് മാത്രമല്ല, ഫിസിക്സ്, അതുപോലെ മൈക്രോവേവ് ഡിവിഷൻ ഇപ്പോഴും അതുണ്ടോയെന്ന് എനിക്കറിഞ്ഞുകൂടാ, അതുപോലെ കമ്പ്യൂട്ടർ ആപ്ലിക്കേഷൻസ്, ഈ പിന്നെ ഇൻസ്ട്രുമെൻറ്റേഷൻ സെൻറ്റർ, ഇതെല്ലാം സെൻറ്റർ ഫോർ സയൻസ് സൊസൈറ്റി, ഇതെല്ലാം അദ്ദേഹത്തോട് കടപ്പെട്ടിരിക്കുന്നു. ഇതുപോലൊരു ചെറിയ ഫങ്ഷൻ പോരാ, കുറേ കൂടെ വലിയൊരു ഓഡിയൻസും വലിയൊരു ഹാളിൽ കൂടേണ്ടതാണ് എന്ന് എനിക്ക് അഭിപ്രായമുണ്ട്. ഇനി അടുത്ത മെമ്മോറിയൽ മീറ്റിംഗ് അങ്ങനെ ആവട്ടെ. അദ്ദേഹത്തിൻ്റെ സ്മരണ പ്രണാമം അർപ്പിച്ചുകൊണ്ട് ഞാൻ നിർത്തുന്നു. നമസ്കാരം.
Thank you, sir, for your touching reflections. Next, I invite Professor K. Shivaprasad, former Vice Chancellor of KTU, to deliver his tribute address.
A very warm good morning to those who have assembled for the fourth memorial lecture in memory of our revered professor and educationist Dr. K.G.Nair. Respected President of the function, guest of honor and main speaker Dr. Seshagiri, former Vice Chancellor Dr. Babu Joseph, and others. Our respected former Vice Chancellor has given a message that we should be giving it in Malayalam, the speech. I can speak in English, but it may take long. So I am restricting myself to Malayalam. Madam എൻ്റെ ചെവി പിടിച്ചു കഴിഞ്ഞു, കൂടുതൽ സംസാരിക്കരുതെന്ന് പറഞ്ഞു കഴിഞ്ഞു. K.G. Nair സാറിനെ കുറിച്ച് പറയുവാൻ ബാബു ജോസഫ് സാർ പറഞ്ഞ പോലെ ധാരാളമുണ്ട്. അത് പറഞ്ഞു കഴിഞ്ഞാൽ ഇന്ന് അന്തിയോളം എനിക്ക് പറയാൻ സാധിക്കും. അതുകൊണ്ട് ഞാനതൊന്നും പറയുന്നില്ല. പക്ഷേ സാറിൻ്റെ ഏതാനും ചില ഭാഗങ്ങൾ, എൻ്റെ സ്മരണയിലുള്ള ഭാഗങ്ങൾ മാത്രം പറയാം. 1975 ഞാൻ എടപ്പള്ളിയിൽ നിന്ന് തൃക്കാക്കരയിൽ വരുമ്പോൾ തൃക്കാക്കര അമ്പലത്തിനടുത്ത് ഒരു ചായക്കട ഉണ്ടായിരുന്നു. ആ ചായക്കടയുടെ പുറകിൽ ഒരു കുടുസുമുറി ഉണ്ടായിരുന്നു. ആ കുടുസുമുറിയിൽ K.G. Nair സാറ്, എനിക്ക് തോന്നുന്നു 1974 അദ്ദേഹത്തിൻ്റെ ആ വിദ്യാഭ്യാസത്തോടും അധ്യാപനത്തോടും അതുപോലെയുള്ള ബാക്കിയുള്ള വിദ്യാഭ്യാസ സംബന്ധിയായിട്ടുള്ള കാര്യങ്ങളിലുള്ള അദ്ദേഹത്തിൻ്റെ ആ ഒരു താല്പര്യം കൊണ്ട് അവിടെ ആ കുടുസുമുറിയിൽ അദ്ദേഹം ഒരു ഗ്രന്ഥശാല സ്ഥാപിച്ചു. ഏതാനും 100-100ഓളം ബുക്കുകളുള്ള ഗ്രന്ഥശാല സ്ഥാപിച്ചു. ആ ഗ്രന്ഥശാലയാണ് ഇന്ന് നിങ്ങൾക്കറിയാം ഈ ഗ്രൗണ്ടിൻ്റെ അടുത്ത്, കോളേജ് ഗ്രൗണ്ടിൻ്റെ അടുത്ത് കേസരി സ്മാരക സഹൃദയ ഗ്രന്ഥശാല. അന്ന് സഹൃദയ ഗ്രന്ഥശാലയായിരുന്നു. അദ്ദേഹത്തിൻ്റെ താല്പര്യം അതൊന്ന് വികസിപ്പിക്കണമെന്നായിരുന്നു. കവിയും എഴുത്തുകാരനും ചരിത്രകാരനും വാഗ്മിയുമായിരുന്ന കേസരി ബാലകൃഷ്ണ പിള്ളയുടെ ആ കുടുംബത്തിൽ നിന്ന് അദ്ദേഹം ഒരു 3-4 സെന്റ് അടിച്ചുമാറ്റി. എന്നിട്ട് ഈ സഹൃദയ ഗ്രന്ഥശാല അത് വിസ്തരിച്ച് കേസരി സഹൃദയ ഗ്രന്ഥശാല, കേസരി സ്മാരക സഹൃദയ ഗ്രന്ഥശാലയാക്കി. അവിടെയാണ് ഞങ്ങൾ 5-10 വയസ്സുള്ള കുട്ടികൾ, സാറ് പറഞ്ഞ പോലെ അദ്ദേഹത്തിൻ്റെ ഒരു പുസ്തകം ഭാഷാ ഇൻസ്റ്റിറ്റ്യൂട്ട് പബ്ലിഷ് ചെയ്ത വെളിയനാട് ഗോപാലകൃഷ്ണൻ എഴുതിയ ഇലക്ട്രോണിക്കം, അദ്ദേഹത്തിൻ്റെ പുസ്തകത്തിൻ്റെ പേരായിരുന്നു. അതിലാണ് ഈ വാൽവുകളൊക്കെ ഞങ്ങൾ ആദ്യമായിട്ട് ചിത്രത്തിൽ കാണുന്നത്. പിന്നീട് റേഡിയോ പൊളിച്ചു നോക്കിയപ്പോൾ ആ വാൽവ് റേഡിയോയുടെ ഉള്ളിൽ കാണുകയും ചെയ്തു. അങ്ങനെ ഈ ശാസ്ത്രത്തിനെ സമൂഹത്തിലേക്ക് കൊണ്ടുവരാൻ ആദ്യകാലം മുതൽ ശ്രമിച്ച ഒരു മഹത് വ്യക്തിയായിരുന്നു വെളിയനാട് ഗോപാലകൃഷ്ണൻ സാറ്. അദ്ദേഹത്തിൻ്റെ ആ എഴുത്തിനുള്ള കഴിവ്, അത് ഞാൻ പിന്നീടാണ് മനസ്സിലാക്കിയത്. എന്തുകൊണ്ടാണ് അദ്ദേഹം ഒരു എഴുത്തുകാരനായത്, ഒരു മലയാളത്തിലെ എഴുത്തുകാരനായത്. അദ്ദേഹത്തിൻ്റെ നാട് നിങ്ങൾ കണ്ടിട്ടില്ലെങ്കിൽ ഒന്ന് പോയി കാണണം. ആരെങ്കിലും ഈ വെളിയനാട് എന്ന ആ ഒരു പ്രദേശം കണ്ടിട്ടുണ്ടോ? കുട്ടനാട്ടിലെ പ്രകൃതി സുന്ദരമായ, ഒരുപക്ഷെ ചങ്ങമ്പുഴ എഴുതിയ മരതകക്കാടുകൾ തിങ്ങി വിങ്ങി അങ്ങനെയുള്ള ഒരു ഗ്രാമമാണ് വെളിയനാട്. ഈ വെളിയനാട് ജനിച്ചവനും ജീവിച്ചവനും ഇങ്ങനെ എഴുതാതിരുന്നാലേ അതിൽ അത്ഭുതമുള്ളൂ. അത്രത്തോളം ശാന്തസുന്ദരമായിട്ടുള്ള, പ്രകൃതി സുന്ദരമായിട്ടുള്ള കുട്ടനാട്ടിലെ ഒരു ഗ്രാമമാണ് വെളിയനാട്. നിങ്ങളെല്ലാവരും അദ്ദേഹത്തിൻ്റെ ഈ ഗ്രാമം പോയി ഒന്ന് കാണണം. കണ്ടിട്ട് വന്നിട്ട് ഞാൻ പറഞ്ഞത് ശരിയാണോ എന്ന് തീരുമാനിക്കണം. ഇനി ഒരു 1975 അദ്ദേഹം ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ്, ഞാൻ ഇപ്പോഴാണ് അറിയുന്നത് 75 സ്ഥാപിച്ചു എന്ന്. കാരണം ഞാൻ 1984 ഷിപ്പ് ടെക്നോളജിയിൽ പഠിക്കാൻ വരുമ്പോൾ അവിടുത്തെ ഒരു കുടുസുമുറിയിൽ സാർ ഇരിക്കുകയാണ്. 1975 മുതൽ 1985 വരെ അദ്ദേഹം ക്ഷമിച്ചുകൊണ്ടിരുന്നു. ഒരു കെട്ടിടത്തിന് വേണ്ടി പല ഡിപ്പാർട്ട്മെൻറ്റുകളും മാറി മാറി അദ്ദേഹം, അന്ന് ട്രസ്റ്റ് ഏരിയയാണ് ഇലക്ട്രോണിക്സ്, ആ മാറി മാറി അദ്ദേഹം താമസിച്ച് 1985 മറ്റാണെന്ന് തോന്നുന്നു ഈ ബിൽഡിംഗ് വരുന്നത്. അതുവരെ അദ്ദേഹം ക്ഷമിച്ചിരുന്നു. ഞങ്ങൾ പഠിക്കാൻ വരുമ്പോൾ ഒരു കുടുസുമുറിയിൽ K.G. Nair സാറ് ഷിപ്പ് ടെക്നോളജിയുടെ ഒരറ്റത്തിരിക്കുന്നത് ഞാൻ കണ്ടിട്ടുണ്ട്. അതിനുശേഷമാണ് അദ്ദേഹം ഇങ്ങോട്ട് വന്നത്. അതിന് തൊട്ടപ്പുറത്ത് അദ്ദേഹത്തിൻ്റെ ഒരു വലിയ റഡാർ, ഈ ഈ ഒരു കൂറ്റൻ റഡാർ അതിവിടെ പ്രദർശിപ്പിച്ചിട്ടുണ്ട്. ആ റഡാർ അവിടെ വച്ചിരുന്നു ഷിപ്പ് ടെക്നോളജിയുടെ സൈഡിൽ. എന്നിട്ട് ഈ റാഗിങ് സമയത്ത് ഈ ഷിപ്പിലൊരു എക്യുപ്മെൻ്റ് ഉണ്ട്, റഡാർ. അപ്പോൾ ഞങ്ങളുടെ സീനിയേഴ്സ് ഞങ്ങളെ റാഗ് ചെയ്യാൻ വേണ്ടിയിട്ട് ചോദിക്കും, ആ കാണുന്ന സാധനം എന്താണെന്ന് ചോദിക്കും. അപ്പോൾ നമുക്കറിയില്ല. അപ്പോൾ അവരെന്നെ ഞങ്ങളെ പറ്റിക്കാൻ വേണ്ടി പറയും, അതാണ് ഷിപ്പിൻ്റെ റഡാർ. റെഡർ എന്ന് പറഞ്ഞാൽ വെള്ളത്തിനടിയുള്ള ഒരു സാധനമാണ്. ആ കൂറ്റൻ സാധനമാണ് റെഡർ എന്ന് പറഞ്ഞ് ഞങ്ങളെ കൊണ്ട് ഇമ്പോസിഷൻ ചെയ്യിപ്പിച്ചിട്ടുണ്ട്. അദ്ദേഹത്തിൻ്റെ ഞാൻ തോന്നുന്നു മൈക്രോവേവ് റഡാർ അവിടെ ഉണ്ടായിരുന്നു. അത് ഇന്നിവിടെ പ്രദർശിപ്പിച്ചിട്ടുണ്ട്. ഒരു പക്ഷേ ഇങ്ങനെയുള്ള റഡാറുകൾ ഇനി ഈ ലോകത്ത് കാണുമോ എന്നറിയില്ല. അത് പ്രദർശിപ്പിക്കണം. അദ്ദേഹത്തിൻ്റെ സ്മരണ അവിടെ നിലനിർത്തണം. 1990 ഞങ്ങളെല്ലാം പ്രതീക്ഷിച്ചത്, 89 ഞങ്ങൾ പോകുമ്പോൾ ഡോക്ടർ ഗുപ്ത ആയിരുന്നു വൈസ് ചാൻസലർ. ഞങ്ങളെല്ലാം പ്രതീക്ഷിച്ചത് ഡോക്ടർ K.G. നായർ വൈസ് ചാൻസലറായിട്ട് വരും, ഈ യൂണിവേഴ്സിറ്റിയുടെ മുഖച്ഛായ തന്നെ മാറും. പക്ഷേ അന്നത്തെ ചാൻസലറായിരുന്ന ഡോക്ടർ സ്വരൂപ് സിംഗ് അത് തെറ്റിച്ചു. അദ്ദേഹം ആരെയോ കൊണ്ടുവന്നു. അദ്ദേഹം ഈ പിന്നെ വന്ന K.G. നായർ പ്രതീക്ഷിച്ചെടുത്ത സ്ഥലത്ത് വന്ന ആ വൈസ് ചാൻസലർ അദ്ദേഹത്തിന് കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയുടെ വികസനത്തിന് വേണ്ടി കാര്യമായിട്ടൊന്നും ചെയ്യാൻ സാധിച്ചില്ല എന്ന് ഞാൻ ആരോ പറഞ്ഞ് കേട്ടിട്ടുണ്ട്. ഒരുപക്ഷെ K.G. നായർ സാറായിരുന്നു 1990 മുതൽ 94 വരെ ഈ സർവകലാശാലയുടെ വൈസ് ചാൻസലറെങ്കിൽ ഈ സർവകലാശാലയുടെ ഇന്നത്തെ മുഖമായിരുന്നിരിക്കില്ല വരുന്നത്. അദ്ദേഹത്തിൻ്റെ നമുക്ക് അദ്ദേഹത്തിനെ എനിക്ക് പറയാൻ പറ്റില്ല, കാരണം അദ്ദേഹത്തിൻ്റെ പ്രവർത്തനം അന്ന് തന്നെ അറിയാം. ലോകപ്രശസ്തനായിട്ടുള്ളൊരു അധ്യാപകനും വിദ്യാഭ്യാസ വിചക്ഷണമായിരുന്നു. കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയെ അദ്ദേഹം മാറ്റിമറിച്ചേനെ. പക്ഷെ അതിനുള്ള ഭാഗ്യം ഈ കൊച്ചിൻ യൂണിവേഴ്സിറ്റിക്ക് കിട്ടിയില്ല. അദ്ദേഹം വേറൊരു കാര്യം കൂടി പറഞ്ഞിട്ടുണ്ട്, എന്നോട് നേരിട്ട് പറഞ്ഞിട്ടുള്ളതാണ്. ഇതിനടുത്തുള്ള തൃക്കാക്കര അമ്പലത്തിൽ പണ്ടൊരു ശാപം കിട്ടിയിട്ടുണ്ട്, ഒരു ബ്രാഹ്മണൻ്റെ ശാപം കിട്ടിയിട്ടുണ്ട്, ഒരു കഥയുണ്ട്. ആ ശാപം തൃക്കാക്കരയ്ക്ക് ഉണ്ടാകും. അത് മാറ്റുവാൻ ശിവപ്രസാദിൻ്റെ കഴിവിനനുസരിച്ച് ശ്രമിക്കണമെന്ന് എന്നോട് അഭ്യർത്ഥിച്ചിട്ടുണ്ട്. നമുക്ക് അതിനുവേണ്ടി ശ്രമിക്കാം. ഈ സർവകലാശാലയെ ഒരു വലിയ സ്ഥാപനമായിട്ട് ഉയർത്താം. അതിനുള്ള ശക്തി ഇതിനുണ്ട്. ഈ 1985 ഈ ഒരു ഡിപ്പാർട്ട്മെൻറ്റ്, മാഡം സമയമുണ്ടല്ലോ, ഈ ഡിപ്പാർട്ട്മെൻറ്റ് സ്ഥാപിക്കുമ്പോൾ ഇങ്ങനെ ഒരു ഓഡിറ്റോറിയം ഇവിടെ ഉണ്ടാക്കുക എന്നുള്ളത് അദ്ദേഹത്തിൻ്റെ മാത്രം ആ ഒരു താല്പര്യവും അദ്ദേഹത്തിൻ്റെ ബുദ്ധിയാണ്. വേറെ എവിടെയുണ്ട് ഇങ്ങനൊരു ഓഡിറ്റോറിയം? ചെറുതാണെങ്കിലും വളരെ നമുക്ക് കാര്യങ്ങൾ കേൾക്കാനും കാണാനും പറ്റുന്ന ഒരു നല്ല ഓഡിറ്റോറിയം. അദ്ദേഹത്തിൻ്റെ തനത് ശൈലിയിൽ ഇൻഫ്രാസ്ട്രക്ചറും ഹ്യൂമാൻ റിസോഴ്സസും അദ്ദേഹത്തിൻ്റെ 2 മേഖലകളായിരുന്നു. എനിക്ക് വളരെ സങ്കടകരമായിട്ടൊരു കാര്യമുണ്ട്. ഞങ്ങളുടെ ഡിപ്പാർട്ട്മെൻറ്റിൽ ഒരു വിദഗ്ധനായിട്ടുള്ള ഒരു ഇൻസ്ട്രുമെൻറ്റേഷൻ ഉദ്യോഗസ്ഥൻ വന്നു. ആ ഉദ്യോഗസ്ഥനെ ഞങ്ങളെ പഠിപ്പിച്ചിട്ടുണ്ട്. കുറച്ച് നാൾ കഴിഞ്ഞപ്പോൾ ഇതേ ഇലക്ട്രോണിക്സിൽ അദ്ദേഹം പ്രത്യക്ഷപ്പെടുന്നു. മുരളീധരൻ എന്നാണ് പേര്. അവിടെ നിന്ന് മുരളീധരൻ K.G. നായർ സാറ് അന്ന് അവിടെ ഉണ്ടായിരുന്ന ഹെഡ് ഓഫ് ദ ഡിപ്പാർട്ട്മെന്റ് പത്മശ്രീ പരമാനന്ദനായിരുന്നു. പത്മശ്രീ പരമാനന്ദനെ പറ്റിച്ച് മുരളീധരനെ ഈ ഡിപ്പാർട്ട്മെന്റിലേക്ക് കൊണ്ടുവന്നു. നമുക്ക് വലിയൊരു നഷ്ടമാണ് അന്ന് വന്നത്. അങ്ങനെ പലതരത്തിലും ഇൻഫ്രാസ്ട്രക്ചറിലും ഹ്യൂമാൻ റിസോഴ്സസിലും ഇത്രയധികം താല്പര്യവും അതിനുള്ള കപ്പാസിറ്റിയുമുള്ള ഒരു മനുഷ്യൻ ഈ കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയുടെ ചരിത്രത്തിലുണ്ടായിരുന്നില്ല. അദ്ദേഹത്തിനെ അനുസ്മരിക്കാം, അദ്ദേഹത്തിൻ്റെ പാതകൾ പിന്തുടരാം. നമ്മളുടെ ഭാവി വളരെ ശുഭകരമായിട്ടേ എന്ന് ആശിച്ചുകൊണ്ട് അദ്ദേഹത്തിൻ്റെ സ്മരണ നിലനിർത്തിക്കൊണ്ട് നിർത്തുന്നു. നമസ്കാരം.
Thank you, sir, for your inspiring words and remembrance. We now invite Sri Rajan Thuvara, noted writer and representative of Professor Nair's family, to share a few words with us. Over to you, sir.
ഞാനും മലയാളത്തിലാണ് സംസാരിക്കുന്നത്. ചിറ്റപ്പൻ്റെ ഏറ്റവും ഇഷ്ടപ്പെട്ട ഭാഷ മലയാളം തന്നെയായിരുന്നു. അദ്ദേഹം ഇംഗ്ലീഷിൽ ചിന്തിക്കുകയും എഴുതുകയൊക്കെ ചെയ്തിട്ടുണ്ട്. പക്ഷേ മലയാളത്തിൽ എഴുതാനായിരുന്നു അദ്ദേഹത്തിന് ഏറ്റവും ഇഷ്ടം. നേരത്തെ ഡോക്ടർ ശിവപ്രസാദ് പറഞ്ഞ പോലെ വെളിയനാട് സുന്ദരമായ ഗ്രാമം തന്നെയാണ്. ആ സുന്ദരമായ ഗ്രാമത്തിലെ ഒരു സുന്ദരിയാണ് ഞാനും വിവാഹം ചെയ്തത്. അതുകൊണ്ട് വെളിയനാടുമായിട്ട് എനിക്ക് വളരെ അടുത്ത ബന്ധമുണ്ട്. വെളിയനാട് വളരെ അതിവിദൂരമായ ഒരു ഗ്രാമമായിരുന്നു വെളിയനാട്. ഇന്ന് കുറച്ച് മാറ്റങ്ങൾ വന്നിട്ടുണ്ട് ആ ഗ്രാമത്തിന്. പക്ഷേ ഡോക്ടർ K.G. നായർ ജീവിക്കുന്ന കാലത്ത് അദ്ദേഹത്തിൻ്റെ ബാല്യകാലം എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ വെളിയനാട് വളരെ അല്ലൽ ഉള്ള ഒരു ഗ്രാമമായിരുന്നു. അവിടെ നിന്നാണ് അക്കാദമിക് മികവുകൾ നേടി കൊച്ചിയിലെത്തി. കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയിലെ ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ് HOD ആയി. അതിനുശേഷം വളരെ പ്രശസ്തമായ സ്റ്റിക് എന്ന സ്ഥാപനം നിർമ്മിച്ചു. പിന്നീട് അദ്ദേഹത്തിൻ്റെ ബ്രെയിൻ ചൈൽഡോ അല്ലെങ്കിൽ അദ്ദേഹത്തിൻ്റെ മാനസ രൂപമായിട്ടുള്ള CSIS അദ്ദേഹം നിർമ്മിച്ചു. മരിക്കുന്നതിന് ഏതാണ്ട് ഒരു 2-3 മാസം മുമ്പ് വരെ പോലും അദ്ദേഹം CSISനെ കുറിച്ച് ഓർത്തിരുന്നു. അത് പറയാനുള്ളൊരു കാരണമുണ്ട്. പലപ്പോഴും അദ്ദേഹം CSISലെ കൺസ്ട്രക്ഷനെ കുറിച്ചോ അല്ലെങ്കിൽ മറ്റു ജോലികളെ കുറിച്ചോ ഇടയ്ക്കിടയ്ക്ക് പറയുമായിരുന്നു. അവിടെ എന്തൊക്കെ കുറവുകളുണ്ടെന്ന് നോക്കാൻ ഇടയ്ക്ക് എന്നോട് പറയുമായിരുന്നു. അതൊക്കെ അബോധത്തിലാണ് പറഞ്ഞിരുന്നതെങ്കിലും അദ്ദേഹത്തിൻ്റെ മനസ്സ് ഉറപ്പായിട്ടും CSISലായിരുന്നു. അദ്ദേഹത്തിനെ കുറിച്ചുള്ള എൻ്റെ രസകരമായ ഓർമ്മകളുണ്ട്. അദ്ദേഹം ഇവിടെ ജോയിൻ ചെയ്യുമ്പോൾ, അതായത് ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റിൽ ജോയിൻ ചെയ്യുമ്പോൾ മുണ്ടശ്ശേരി ആയിരുന്നു വൈസ് ചാൻസലർ. അപ്പോൾ മുണ്ടശ്ശേരിയുടെ മുഴുക്കിനെ കുറിച്ച് അദ്ദേഹം വളരെ വിശദമായിട്ട് സംസാരിച്ചിട്ടുണ്ട്. മുണ്ടശ്ശേരിക്ക് ഇദ്ദേഹത്തെ വളരെ ഇഷ്ടമായിരുന്നു. ഇതിനെക്കുറിച്ച് ധാരാളം സംസാരിക്കുമായിരുന്നു. അതുപോലെ തന്നെ മുണ്ടശ്ശേരിയെ കുറിച്ച് പറയുമ്പോൾ തന്നെ MV പൈലിയെ കുറിച്ചും പറയാനുണ്ട്. കാരണം ഡോക്ടർ MV പൈലിയുടെ കൂടെ ഒരു തവണ എന്നെ പരിചയപ്പെടുത്തി. ഡോക്ടർ MV പൈലിയോട് സംസാരിച്ചത് വേറെ ഒന്നുമല്ല, അദ്ദേഹത്തിൻ്റെ ആത്മകഥയുടെ മലയാള ആവിഷ്കാരം വേണമെന്ന് പറഞ്ഞിട്ടാണ്. അന്നാണ് ഞാൻ മനസ്സിലാക്കിയത് ഡോക്ടർ പൈലിക്ക് കൂടെ ഈ ഇലക്ട്രോണിക്സ് ഡിപ്പാർട്ട്മെൻറ്റ് ലോഞ്ച് ചെയ്യാനുള്ള വലിയൊരു സപ്പോർട്ട് നൽകാനായി കഴിഞ്ഞു എന്നുള്ളത്. അദ്ദേഹത്തിൻ്റെ നേരത്തെ മറ്റ് പ്രസംഗകർ പറഞ്ഞതുപോലെ ഡോക്ടർ K.G. നായരെ കുറിച്ച് യിരുന്നു. അത് വിശദീകരിച്ചില്ല. മറ്റൊന്ന്, ഈ കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയിലെ വളരെ പ്രഗത്ഭനായൊരു വൈസ് ചാൻസലറെ ചേർത്തുകൊണ്ടൊരു നോവൽ എഴുതാൻ ശ്രമിച്ചു. ആ നോവൽ ഏകദേശം 3/4 ഭാഗമായിട്ട് അത് റീഎഡിറ്റിംഗ് ഇറക്കാൻ തീരുമാനിച്ചാൽ അദ്ദേഹം പറഞ്ഞു വേണ്ട, അത് യൂണിവേഴ്സിറ്റിയിലെ മറ്റു പലരെയും വേദനിപ്പിക്കും, അതുകൊണ്ടത് വേണ്ട എന്ന് പറഞ്ഞു. അതിൽ അദ്ദേഹം ഒരു കഥാപാത്രമായിരുന്നു. അതിൻ്റെയൊക്കെ മാനുസ്ക്രിപ്റ്റ് എൻ്റെ കയ്യിലിരിക്കുന്നുണ്ട്. അപ്പം അദ്ദേഹം അത് നോ പറഞ്ഞ സ്ഥിതിക്ക് പിന്നീടൊന്നും ചെയ്യാൻ പറ്റാതെ. ഇത്രയും ഓർമ്മകളാണ് എനിക്ക് ഷെയർ ചെയ്യാനുള്ളത്. ഇതൊരു ചെറിയ 4-5 വാക്കുകളിൽ ഒതുക്കാവുന്ന ഓർമ്മകളല്ല അദ്ദേഹത്തിനുള്ളത്. എങ്കിലും അദ്ദേഹത്തെക്കുറിച്ച് ഓർക്കുമ്പോൾ ഇത്രയും പറഞ്ഞില്ലെങ്കിൽ അതൊരു അനൗചിത്യമാവുമെന്ന് തോന്നി. അതുകൊണ്ടാണ് ഞാൻ ഇത്രയെങ്കിലും പറഞ്ഞത്. എല്ലാവർക്കും എൻ്റെ നന്ദി.
Thank you, sir, for those heartfelt words. We now arrive at the most awaited segment of today's program, the Professor K.G.Nair Memorial Lecture. Now, in its second year, this lecture series stands as a tribute to the spirit of science, scientific inquiry and academic excellence of that Professor Nair embodied through his distinguished career. It is indeed a great privilege that an eminent scientist and distinguished leader in defense research, Dr. Duvvuru Seshagiri, scientist H and director of Naval Physical and Oceanographic Laboratory, Kochi. To introduce the speaker to the audience, may I invite retired Professor Anandan, Department of Electronics. Meanwhile, I request all dignitaries to kindly take the front seats as we begin the lecture session.
Good morning to all. It's my privilege to introduce the speaker of this memorial lecture, Dr. Seshagiri. Actually, Professor K.P. Ray Professor of Indian Institute of Technology, Gandhinagar, who has visited this department so many times, and the PhD supervisor of Dr. Seshagiri agreed to introduce the speaker, but unfortunately he couldn't join due to some emergency. That's why I'm standing before you to introduce the speaker. So Dr. Duvvuru Seshagiri, Scientist H, is the director of NPOL, the prestigious DRDO lab in Kochi. So where he is steering the different sonar projects related to advanced technology vessel project known as LTVP platform, P-76 class of submarines and other ship-based and airborne systems. Prior to taking the role of director at NPOL, he was serving as the head of Airborne and Spaceborne Radar Division at LRDA, Bangalore. Dr. Seshagiri began his career at LRDA, Bangalore as a junior scientist. Later, led the radar system team for airborne systems and implemented very long-range radar systems. He was instrumental in the design of India's first active phased-array radar, L-STAR, which led to the development of the primary radar for airborne early warning and control system known as AEW and CS. He is the main architect of AEW and CS primary radar, which is the first airborne detection radar designed to simultaneously track both air and sea targets, capable of monitoring multiple targets at a time. These systems were integrated into the Indian Air Force and have engaged in various exercises and missions of Indian Air Force, including the recent Operation Sindoor. He also served as the project director of Uttam, the indigenous radar used in Tejas light combat aircraft, which is known as LCA. This airborne radar made India self-reliant in airborne radar sector. So by employing the airborne surveillance platform and Uttam active electronically scanned array fire control interceptor radar, India has positioned itself as one of the top 3 nations possessing this advanced technology. Dr. Seshagiri played a pioneering role in making India self-reliant in airborne radar segment. His contributions are recognized by different awards, such as Scientist of the Year Award in 2011, Pathbreaking Research Award in 2020, IETA IRS Award in 2019, and he is also the recipient of the prestigious Scotch Platinum Award in 2016, which recognizes individuals contributing significantly to socio-economic growth, governance, technology, and inclusive development. And he has authored a large number of research publications in national and international journals and conferences. I would like to add just a few words about my guru, Professor K.G.Nair. So as already mentioned by different speakers, Professor K.G.Nair is a popular science writer, administrator, institution builder. But for us, his students, KGN sir, as we usually call him, was a great teacher. Teaching was his passion, which he continued for more than 20 years after his retirement from service. Radar was his favorite subject, which he taught us with much enthusiasm. So the radar which is standing in this compound, as already mentioned, it was his effort to bring it from Bangalore so that the students will get a feel of the actual system. So that way, the topic of today's lecture is very much relevant. And Professor Nair always kept good relationship with NPOL and was very close to the directors during that time, starting from Dr. Atre, Dr. Srinivasan, Dr. Chandar, Dr. Ananthanarayan, and other great personalities. So today we are lucky to have the director of NPOL himself, who is also a radar expert, to deliver the memorial lecture. So I cordially invite Dr. Seshagiri to deliver this talk.
Taking cue from former Vice Chancellor CUSAT Babu Joseph sir, subsequently Sivaprasad sir and Rajan Tuwara, I also would like to speak in my mother tongue. ఎందరో మహానుభావులు అందరికీ నా వందనములు. At the outset, I have to thank Madam Deepthi. When we met at MapCon, I asked her, please give me a chance to talk on radars, because radar being so close to my heart. At this institute, I didn't think that the opportunity will come in this way. Thank you, Madam, for giving me this opportunity. I also, though Professor has left, Professor Babu Joseph, Professor Arun, who also has left, Professor Shivaprasad, the Vice Chancellor, KTU, Rajan Saab, who is a relative of K.G.Nair Nair sir. It is my privilege to stand before you today on sir's fourth memorial lecture. And as I understand, he is also an avid radar teacher, which makes me very happy to talk about radars today. Fortunately, we share at least there is one intersection between our interests. In fact, some time back, there was one program here in the CUSAT about the science in society, where I was also invited, and at the time the chief guest was a student of this institute who was the then DG R&M, Dr. Manu Kurela, and he delivered a wonderful lecture. As I remember, with the children, he started to give a lecture on the big things that DRDO does, but he stopped it and gave an extempore lecture on science in society, which I still remember as one of the gems of lectures I have heard. I'm telling because he is an alumni of your esteemed university. In fact, NPOL is full of alumni of CUSAT. So it gives me then again a lot of pleasure to be here with you today. Thank God I'm not going to speak in Telugu now. I am going to speak in English. So you need not have to worry that you don't know Telugu, or your Telugu is limited to what Tyagaraja has said. Okay. So today I was told, I'm going to talk about some of the sensors for airborne warfare. And Operation Sindoor has shown that what it means to have our indigenous weaponry and indigenous sensors. You know, the most of the war was fought, if you remember, with two weapons and a couple of sensors. And except one, which is the S-400, all the others happen to have been developed in India. That actually shows the Indian industries, basically industries and Indian research power prowess, which has brought us to this stage, where we can today say that we are one of the few countries, as Sir was introducing, we are one of the handful of countries today have all these technologies which make us more or less self-sufficient. We still continue to be one of the major importers, but slowly we are tending to become exporters of defense equipment. And I hope in the near future, and I hope the velocity curve or the acceleration curve which we see, which is also, because I come from Kalman filter background, there may be a jerk and a jerk rate also. Such is the acceleration with which the country is growing today. And I do not think in the way we are going to be importers any further down the line, and we are going to be the next exporters of defense equipment. In fact, I was reading in one of Russell's books, Bertrand Russell, most of you will be knowing. Defense is a misnomer. Because if every country has only defense forces, who is the one who is the offender? So, but, for historical reasons, it is known as defense. And really seeing back, who is the offender, who is the defender, that line is always very thin. You cannot say he is the offender or he is the defender, unless, of course, someone comes from outside the country. But who went first is always a question mark. And so also in the last wars which we have fought, who was the offender, who was the defender, we cannot clearly say. Therefore, it is necessary we should have weapons which are of the offense type too, not just defense. Though I am now today going to talk about defense weapons, not offense weapons, in the sense that I am going to talk about interceptors, not missiles which are, the missiles which I am going to talk about are more interceptor missiles and not the ballistic or cruise missiles which are more used as a offense. So I can. Can you go to the next slide, please? Okay, I thought I'm going to talk about surveillance radars, electronic warfare. CIT is a combined interrogator and transponder. IRST is infrared search and track. MOS is missile approach warning system. And these are sensors which will be in any one of the aircraft which are modern. In fact, our LCA has all of them, because they become, imperative. Without them, which you cannot win. You cannot fly an aircraft any further. You know what? During Operation Sindoor, at 150 kilometers away, there was a kill of a fighter aircraft. A Pakistani aircraft was shot down at 150 kilometers. And I understand one of their AWs, which is a Saab Ericsson, which is from Sweden, which they have purchased, and some of them were given by Saudi Arabia to Pakistan, was shot at a distance of 350 plus kilometers from Indian borders with a cruise missile, not even a interceptor. So, we do not know where we are going to end up today without sensors and weaponry that are going to help an aircraft to fly. So, aircrafts fly no more is a function of how the aircraft is designed, more a function of how the sensors and weapons are designed. A very ordinary aircraft can become a potent aircraft if it has good sensors and weapons. And let us suppose a hi-fi aircraft, Su-30 for example, one of the best aircrafts from the aerodynamics point of view. If its sensors and weapons are not to that extent good, I'm not saying the current ones are bad, I'm telling if they are not good, it will be useless in spite of its high ability to maneuver and high aerodynamics that it has. So today's aircraft is no longer defined by the aerodynamics, but by the sensors and the weapons it carries. And that is what is about the fire control radar. And it is going to help the interceptors to be guided to the enemy aircraft, and I will show in a few videos how it is done towards the end. I hopefully will complete in 45 minutes, so that some videos I'll play, and there is some time hopefully for a Q&A at the end. And don't bombard me with such questions, because all of you are more educated than me, which I cannot answer. So the third part is the imaging radars. Some of the glimpses I will show. You can take an image of a territory from a satellite, which you all are aware of, because all of you use in one way or the other. If you have a Google Earth, let us say, maybe it is a electro-optic image, but it is not necessarily always true. You can have a synthetic aperture image also, which is a RF image. Therefore the radars which are going to be used for such imaging are known as either maritime patrol radars or reconnaissance radars, and such programs are there already in India with a lab called CAPS, which is doing a lot of such work. But the sensors, of course, come from the sensor labs. We also develop a lot of EW, which is the electronic warfare. If you have a radar, the first thing what you want to do, you want to make the radar useless. You want to jam the radar. To jam the radar, you have to recognize that there is a radar. To know that there is a radar, the RWR, radar warning receiver, and the electronic support measure or the electronic intelligence. Knowing that, we can use the last option of electronic countermeasure to jam such radars. Either, there are two types of jammings which I'll come to, but basically it is to make the radar useless. There is also now, even when they are communicating, you can know that they are communicating and therefore can interrupt the communication, which is known as the comment or the CSM. The CIT is where you try to figure out whether it is a friend or a foe. The other aircraft is an enemy or our own aircraft, so that the fratricide can be avoided, is the CIT. And the IRST is an infrared search and track sensor, which can be used. I'll show you some pictures. I also brought some videos from OpenNet, where you can actually see very clearly an aircraft as an aircraft, even at 10 kilometers of distance, not the distances of radars. Radars generally now, today we have ground-based radars of the order of few thousands of kilometers range in India, and airborne radars touching almost 500 kilometers. That is the sort of, that is where we stand as a country today. And when a missile is coming towards the aircraft, it has to know that there is a missile coming towards it, so that it can come out of such a threat. And to know such a missile approach, a sensor which is used is known as the missile approach warning sensor. It can use any type of detection methodology. It can use shock wave, it can use the IR, it can use the RF signature. Any one of these three techniques it can use to figure out that there is a missile coming towards. Just a brief history to start with of EW. EW is the area where I have not worked, but a radar man has to know what is the EW, because the radar always tries to come out of the jamming and see that no one detects it. On the other hand, the EW always tries to keep jamming the radar. There is a, what you call a cat and mouse game continuously being played by these two players. So the first time when in 1904, this war is very interesting war with what has happened between Russia and Japan, because it was for the first time a Asian force has defeated, other than, this is not the first time in the modern warfare, let us put it that way, that Asian force has defeated a European force. It happened in 1904 when Japan defeated Russia. I said modern warfare because here in Kolanchal, what is his name, Martanda Varma has defeated the Dutch and completely destroyed the Dutch capability to have a kingdom in the east. So it is not necessarily the first time. So it is in the modern warfare sense, it is the first time. Japanese have used communication techniques which the Russians have jammed for the first time. That was how EW came into picture. But the basic one was done by a great man called Reginald Jones of Britain. Most of the development of EW or radars or whatnot, or aircraft, everything happened in Britain during the Second World War and the 19th century. And there is a famous general by the name Montgomery. How many of you would have heard? I do not know. Montgomery. So he was a very methodical man. And the general of America at that time, though was Eisenhower, but the one who gave the third thrust towards Germany is by a man by the name General Patton, who was the general of the Third Army, which is a very famous army. So one day, it seems he was, it is 1944-45 times, Germany already lost. So he was at the entry of Germany, Patton was, going at a breakneck speed, almost like 100-150 miles per day, unimaginable in those days, probably today too. To get into a country 150 kilometers, defeating all the forces is not a joke. So he is going at such a speed, and Patton was, Montgomery was not very keen or happy with the techniques of Patton, and he goes to Churchill and says, I don't like the way he is doing the war or he's fighting the war. Then Churchill tells, after 5 minutes of thinking, I think we are losing out, because today the point is speed and speed and speed, which we are not having and he has. Our time as a world leader ended today, and the world leadership is going to pass on to America. This happened in 1940, 44, 45 time, as predicted by Churchill. And all you know that what happened after 2-3 years. Britain is nowhere. Britain lost all its colonies, including ours. And suddenly it was out of race along with Germany. But most of the development happened in England, which today it looks like, how England could have done such things, looking at what is England today. But it was Reginald, who was also known as the Wizard of the War, in a battle called Battle of Beams. Beam is a radar beam. So he was able to pick up the radar beam and jam it. And a beautiful technique was used by the Germans. Actually, they had to navigate an aircraft to go to a particular place and bomb it. Now you have to know how do you actually navigate in a country which is like, let us say, they cannot go in the day. They always go in the night, because those days visibility was not through radars. So there was no visibility that the aircrafts are coming. Therefore, the chances of bombing the enemy city was high. So Germany was therefore always going and bombing in the nights. Now it was how do they were all wondering how they are going exactly to that city and bombing. This guy predicted was they are probably using RF. And how they are doing, he did not know, but this is how the ingenious Germans have done. Next slide. They took an antenna which made some angle, what you can see there at the bottom. There, that the antenna which is making a small angle, and two beams were synthesized. The exact cross section of that was pointed towards the city that has to be bombed. And of course, range is always known because you know how many kilometers you have flown or nautical miles you have flown. And then on one beam, they transmitted ... and another ... Exactly on the line, center line, as is shown in this thick line, the two energies are equal, and he gets a continuous wave like a sine wave. What was not otherwise a sine wave, he now hears it as a sine wave, and therefore could easily align to the line and go along the line and bomb the cities. Trivially simple, but the ingenuity is unbelievable, at least for me, how someone would have thought like that. Now what this guy did, he went in a car to figure out, because in a car you can listen to RF if you have an antenna on top of the car. You cannot, because the line of sight will not permit, because it has a huge curvature. So he could not, and he tried out to, those days it was very difficult to get an aircraft. Somehow he could manage an aircraft and fly. When he could hear to these two beams, then what he did was simply pump from ground some energy, which is again a dash, but in a different direction. Now they were going to some other place, an open field, and dropping their bombs. All their bombs were wasted. So this was the first time a EW was successfully used in World War II. So he is known as the father of EW, Reginald Jones. Next slide. The same is the story of radars. Okay, before I go there, you know what is an IFF. All of you know IFF. You would have seen it day in, day out, whether you recognized it or not. When you fly, invariably the IFF is the one which is actually guiding the aircraft, not the radar. In fact, to the extent that, you have a radar 24 site. If you open radar 24 site in the net, you will see all the aircraft which are flying anywhere in the world. And that is thanks to the CIT, and now we have more advanced techniques also. But this is the basic measure which is used even today when you go for a war to know whether the other aircraft is our friend or foe. By knowing the signature, when you communicate and they communicate back. So it's more of a communication equipment, but it is also known as a secondary surveillance radar. Okay. So you pump in some energy, goes, hits the radar will, its own transponder will send back that I am here. That's called mode S. Anyway, there are multiple modes. One of the mode is mode S. Next. And this actually, if you are wrong, you can be, okay, this is about laser pods. Now let us suppose there is a missile which has been fired against this aircraft. It is picked up by some means and the information is passed to a fighter aircraft which is nearby. He can use a laser pod to actually, burn the missile. It is, such laser pods are there in multiple aircrafts today. Now let us see how he is going. I mean, a little longer video from open source, but you can see that it is lasing and थोड़ा आगे बढ़ाओ. There's the lasing, and it finished the, it's gone. That's how the interception happens by lasing. Next slide. Okay, the other part is the radar, which is what I'm going to talk. The first aircraft detection was done by binoculars. They used to see and figure out whether the aircraft is coming or not, maybe a few kilometers. The second one is a sonar, is here. This is you can see actually there are 4 such horns, 2 here in the vertical and 2 here in the horizontal plane. And these 4 are used to detect aircrafts maybe a few kilometers, again maybe 10 kilometers. But someone can guess why there are 4 horns. Yeah, when you have 2 horns, like you have 2 eyes, you know the depth. Otherwise, you do not know. So angle information can be known if we have 2 horns. And that's how today's radars also do in the monopulse case, that they use 2 halves of an antenna to find. So the technique is, all techniques what are developed at one point of time, again we will come back in some way or the other. I am going to show multiple of them. This is a parabola. This is a parabolic reflector, and parabola has a property that its eccentricity is 1. Therefore, it goes to, all the energy goes to one point known as the focus, and they built a huge such dome to increase the range of this sonar. This is also a sonar used in the Second World War, just beginning of the Second World War. But what happened was, there was a milk cart coming in the way, and that noise was picked up as that of a aircraft. There is no way to know. So they thought that it is a useless device. And then came the RF. Next slide. These are non-RF techniques. The RF techniques, the first one is from a movie where they put a parabolic reflector and they thought that they can destroy anything. I have a video, but it did not bring it. Concentrate the energy and burn it. They were thinking that they can concentrate, just like in the lasing case, they can concentrate the energy onto an aircraft and burn it. Did not happen though, because the energy required is too very high. It's not possible. But again, it is back today. When there is a drone attack, the drones are destroyed by such a technique. This is known as EM pulse. Pulse is a very high energy thing. But in any case, today we use very high energy electromagnetic waves to destroy drones up till maybe a couple of kilometers, which is sufficient to, for in the drone's case. Then came the FM radar. They had a FM station close by, FM radio station. Those waves, they went and hit this is a famous man who did the experiment, I'll tell the name. And what they saw is there is a jump in the dot, indicating that there is a aircraft. That is the first time they understood that RF energy can be used to detect aircraft. And they built this huge bistatic system, what you see here. And the man who built that is a man by the name Watson Watt, a very famous one, most of you would have heard. And his assistant called Wilkinson. That's why we have Wilkinson. Wilkinson, for anyone in RF will know his name. But otherwise, first radar was a bistatic radar, and then it became monostatic. Today we have multistatic and MIMO. Again, the bistatic is coming back in different ways. One more interesting thing is here, when they tried it out for the first time, they found that it was absolutely not picking up any aircraft, except exactly on top. All the Air Force officers of RAF, they said this is a useless device and walked away, except one air marshal, I forgot his name, and he said, continue your research. So money was pumped in, they continued their research, and finally they could pick up targets up till 100 nautical miles, about 185 kilometers. The point is, we still face the same thing even today. RAF in 1944 and our own users today, they are not very different. After all, human being doesn't change in a century. We also face, we have great officers who help us in development, many officers who try to pull us down. I had both sides. It reminds me of one of them. His name is Wing Commander Kalia. When we first made a phased array radar, as I was reading out, L-Star, which was the first phased array radar, we opened it and we flew one fighter aircraft against it. There was not one detection on the radar screen. Then he said, no problem, don't worry, it is a first experiment, you continue your development. What we found, one team thought, in coordinate systems, you have right-handed coordinate system and a left-handed coordinate system. All of you are aware of that. And most of on Earth, we use right-handed coordinate system. So you have X, Y, Z. So we thought the coordinate system is NED, north, east, down. So down is positive. The antenna guy thought down is negative, up is positive. So he put the beam down, whereas we were thinking it is going up to the aircraft and we did not pick it up. Then if we figured out, and of course, after that it started working. We also had one more officer, because I remember the other officer, the name is not important. Every one problem he will blow it into a huge big problem. We were flying one day on AWNC. It was a resolution sortie. So I was sitting and one who was, my colleague was also sitting. He said, we will tweak one parameter. Let us see whether we will get the detection, because two close by targets, if you are using constant false alarm ratio for detection, one will interfere with the other. So let us bring down the constant false alarm ratio a little for this sortie. I said, let us go ahead. Then this guy came and said, we were already airborne with two, I will show you that sortie. With two fighter aircrafts also airborne, to see that we are able to track the resolution or not. Resolution means you have to tell the two aircrafts that there are two aircrafts if there are two aircrafts flying pretty close by. Then he said, I am calling off the sortie because you have changed the parameter. We had a lot of altercation and we had to make him keep quiet. But there are such officers also who can become an impediment. There are officers also who actually help us when it means a lot. When we require them to help us a lot, and I have come across many such officers who have helped us. So, because you are on YouTube, I would like to thank them all. Next. So when a countermeasure is there, obviously radar cannot keep quiet. Someone is jamming you, someone is looking at you. You should not make him look at you. You should not make him jam you. So for every electronic countermeasure, which is to say that the EW is going to jam you, ESM is going to pick you, we have a counter measure. Means if he is jamming you, how to come out of the jamming, that you have to see. So now you have different types of jammings, like standoff jamming, they say. A standoff jammer is not the same aircraft. There is another aircraft which is jamming, and it is trying to come through the side lobes of the antenna. So what we do is we put a null in the direction, because we know the direction of the jammer from the correlation of the noises, and we put a null in the direction of the jammer and remove it. Also, there are multiple techniques like music and spirit. I put them here because the man who developed these is a man called, they were different English people, but the basic one was Thomas Kailath, who is an Indian. And the man who helped him and later was with him in doing all these eigenvector methods is Professor Paul Raj, who was in NPOL. The other one is the self-protection suite, where when there is a jamming happening, jamming is happening from our own aircraft, in the sense that the aircraft which we are tracking is also the source of the jamming. Then it is known as a self-protection suite. In that case, we don't track it by the radar. We just track it with the radar listening only. We don't send pulses. We hear to what is coming from the space and keep tracking the aircraft. Now, because we are doing passive, we don't know the range, but we do know the angles. Therefore, we can continue tracking. So, you have anti-radiation missiles. Some, I do not know, I have not brought an example of that. Is also a countermeasure. A missile is locks onto the radar radiation and goes towards the radar. And we have a few of them developed in India, Rudram series, which they can lock onto a radar and destroy the radar. So what we do is we develop decoys to the radar, which mimic the RF, but they are not the radar, and pull the missile away. That is how the ARMs are taken care of. Now, for denying the ASM to see, the radar has changes the frequency very rapidly so that the other fellow cannot see it. Or another technique is it has many different types of waveforms which randomly picks up. It is almost impossible if you do not know the frequency and the waveforms which are changing at such high rate to pick them up. Next. And to break the lock, and let us suppose there is a missile which is fired at you and it has locked on. Locked on means you would have seen in the movies that it actually, the seeker picks up the target, or the aircraft radar picks up the target. He knows that someone is tracking you through the ESM. Then they know that there is a lock on. So now they have to come out of the lock on. So if the seeker, the one which seeks on the missile, there will be a sensor called seeker. That seeker, if it sees that it is locking on with the IR seeker, it assumes, it doesn't see, it assumes, then flares comes out of the aircraft. I'll show you how the flares come out. And these flares have the similar IR signature like the aircraft, and the missile will move towards the flares, moving away from the aircraft. And if it is a RF seeker, like a radar, the aircraft throws out small aluminum pieces which have some RCS and try to pull away the missile away from the aircraft. And for the ARMs, which because again, as I was saying, on aircrafts you cannot have decoys, so we'll have very low power output. So they are known as low probability intercept radars. Next slide. This is an example of flare. Run the video. These are the flares. You can see they are dispensing the flares which will attract the IR seekers. Next slide. The different, and chaff is also like that. You can see, give me a minute. Now once the missile launch is known, that is a flare. Again a flare. Now you see these are the chaff. The chaff actually is aluminum pieces which will have the radar, no longer can see the aircraft. They'll see the chaff instead and move away from the aircraft. Next slide. Okay, a little forget it. When a radar pulse is sent, it comes back after some time, and the time delay is used to measure the range of the radar. Next slide. And the radar functions is that it can do actually the name of the radar itself is radio detection and ranging. So it does the ranging. It also measures the range rate by knowing the Doppler. It measures the angle also to I will show you, I think I have a video where we were tracking a ground moving target, a jeep on a road which was 100 kilometers away. The road was 100 kilometers away from the aircraft, and it was moving on a road which was 30 meters wide. From 100 kilometers, we have to show that it is going on that road. That means it should have an accuracy of how much? 30 divided by 100 kilometers. That's about 0.3 milrad. 0.3 milrad is, most of you know what is a milrad. Milrad is 1/20th of a degree or 0.05 degree, and 1/3 of a milrad is 0.02 degrees. Unimaginably thin. Okay. That's the sort of direction of arrival accuracies that we can measure today. We can also know the target size. That means whether it is a bomber or a fighter or a aircraft carrier, name it based on the bigness or hugeness of the object, we can tell what is the object. Then we can also detect the moving parts. Like a aircraft has, in radar, you can also detect the jet engine's vanes. When the jet engine rotates, the vanes will have a certain Doppler, which is different from the Doppler of the main body. You can pick up those small Dopplers and know how many vanes are there. Therefore, what is the sort of aircraft? It's known as NCTR, non-cooperative target recognition, but is feasible today. Next. And the types of radars, all of you know, they're ground-based, shipborne, airborne, now spaceborne also. And spaceborne radar of late, ISRO has very famously put a Indo-US collaborative, I don't know, NISAR or something into the space. That has a resolution of about 1 or 2 meters on the ground. We also have one such program where we also can look at such. I will show you some pictures. We do on the aircraft, which is much more difficult. We have stationary radars, mobile radars, search on move radars. Aircraft is search on move, but in ground also you can have search on move by putting it on in a tank or any other vehicle. We have shipborne radars, airborne radars. Again, in airborne we have surveillance radars, AWC class, which about 500 to 800 kilometers. Fire control radars for fighters with about 300 kilometers. Synthetic aperture radars, now we have synthetic aperture radars up till 1000 kilometers from the space. But though on Earth you will have about 200 plus kilometers and spaceborne. Next. Can you please go to the next slide? And in the airborne radar itself, there are many classifications. You have surveillance radars, like you can have a radar on a AWNC, let us suppose, it's a surveillance radar. You can have it on a balloon. It's called aerostat radar. It will be around 4.5 kilometers altitude, tethered to bottom at the ground, but huge ranges it will have. Then you have fire control radars like Uttam, which give very good accuracies at relatively short ranges. Imaging radars, weather radars. Weather radars are, all your aircraft when you are flying have weather radars on it, but they have to know the weather condition. Secondary surveillance radars, as I was telling, the IFF and multimode radars today, which cover all the top, then they are superset of all the above. And Uttam is a multimode radar. and I will show a video at the end. Next. And the functions of airborne radar include surveillance, fire control, imaging, navigation also they can do, in the sense that when you are flying on a terrain, what is the altitude of the terrain, or in the front, how much distance you can fly before the mountain is going to come in the way. Things like that you can know. It's known as terrain avoidance or terrain following. You can do electronic warfare with radar. Radar itself can be an electronic warfare device. Not you can share the aperture for both of them. It's called shared aperture. Maybe in your Anna theory you would have studied it. Target classification using inverse synthetic aperture radar, where the movement of the body is used to generate that micro Doppler which we are studying, and trying to figure out the target. I'll show you some images. Next. And the key technologies for airborne radar include, today at least, the phased array antenna. And phased array antenna, in your radar class you would have studied. A TR module is a part of the antenna. The receiver, which is also a part of the antenna, but multiple other modules will be there beyond the antenna. The signal processor, actually, at the end, at the front of the antenna, the signal strength that we receive is of the order of minus 150 to 160 dBm. dB milliwatt. You can imagine how much is the energy. And the noise that we are going to compete with is of the order of minus 100 dBm. So the signal is some 50-60 dB buried in noise, which because of the array processing and the signal processing, we pick it up to about 70 dB, let us say. The 70 dB because you should be at least 10 dB more than the noise. So your processing gain is of the order of 70 dB today. A huge number. Radar controller, which actually controls everything in the radar, and the radome, which in itself is a huge technology because it's a lot of materials and things like that in the radome design. Multiple labs in DRDO work only on the radome. Next. And some of the surveillance in the platforms globally. The one which is, I didn't bring that picture, the one which is the first radar on aircraft is Hawkeye of America. It's a wonderful radar, and now almost 50 years into the service. They have this J stars. There is you can see the radar on the bottom. This is what Pakistan has, Saab 2000, and that is the radar on top of it. This was what was shot down by Indians in the Op Sindur. Falcon AWACS, this is an Indian AWACS but imported from Israel on a IL-76, huge aircraft, IL-76 or 78. And this is Wedgetail of Australia, one of the modern AWNCs today in the world. And this is Boeing Sentry E3. The rotodome actually rotates. The one idli on top rotates, and the antenna along with it rotates. This is a fixed antenna, and this is a rotating one. Okay, now this is about a brief about general radars. Now I will talk specifically about the primary radar development in India, which is also we call it as Netra, and therefore eye in the sky. The main fundamental challenges for any ground-based radar is, as I was telling, the LOS, and they can also use the features on the ground to hide behind and come. Generally, they do this. They fly very low when they want to bomb enemy countries, as low as 30 meters to 100 meters. Now, when they are flying so low, a ground-based radar doesn't detect it because it is not visible beyond the LOS. So invariably, it will be that you will not know till they come very close by to you because of the terrain masking, the LOS limitation, and therefore very low reaction time for the interception of that. Now you see, if you have a airborne radar like such, you can pick it up because these LOS limitations are not there for a airborne radar. also the terrain masking is not feasible. Therefore, you pick them up and then you can, for the flying so low, you require a terrain avoidance and terrain following. I was telling that Uttam has that mode also, or a fighter aircraft radar has that mode also, where you can fly very low, and when there is a mountain in front of you, automatically it will tell you, you pick up your altitude. So it is feasible to fly very low even in a mountainous terrain. So it is going to increase your LOS using a airborne radar, which is flying at an altitude of around 25 kilo feet, 8 kilometers, and it will give you a long range, almost to the order of 300 kilometers on LOS. But if the aircraft is flying at an altitude of another 8 kilometers, it means it can see it at around 600, 700 kilometers a day. Incidentally, the like a sound wave bends, so also electromagnetic wave. So because it bends in the atmosphere, you get more range than expected. So if your LOS is 300 kilometers, because of the bending of the ray, you are going to get about 50, 60 more kilometers in range. And that's how it happens. It picks up and okay, this is the operational scenario of a AWNC, where it actually picks up the targets, and that information is passed on to a satellite. There is a SATCOM. You can see a bump here. That bump is a SATCOM antenna there, and that sends that information to satellite. Satellite will send to a ground exploitation center, which is also known nowadays. We have IACCs, which you would have heard about, Indian Air Force's command control system. All the radar information in the country will come to a central node. They also have the information coming from all the missiles that are available, and therefore can be intercepted. You used to intercept any enemy aircraft that is flying. And this is because we were doing for the first time, we had to do so many new things to start with, which is like development of a first phased array radar, which was read out while they were reading out my biodata. A long range multi-target multi-mode capability. It can track more than 1,000 targets at a time. So many aircrafts are not there in, of course, not there in Pakistan has something like 300, 400 aircraft, and China has around 1,200 to 2,000 aircraft. So it has more capability than Pakistan, China put together to track so many targets at a time. And it is fully active phased array radar, so that you are no longer steering the beam like in a ATC radar, which you see it rotates. It takes about 6, 10 seconds to come back to the same place. You can come back to the same place almost instantaneously. That's why you require a phased array technology, and this radar has that such technology. The antenna is the black one on top of the aircraft. It's about 10 meters of length, of which some 7 meters is the actual radar length. It is a air-cooled radar. As you fly, there is an inlet to the air here. You can see that orifice. The air comes in, and the heat, what is generated by the TR modules or the radiating elements, is taken away and thrown out in the air going out from the orifice at the back. On top is the IFF element. The actual radar element, and bottom is the IFF element. So it has both radar as well as IFF in the same antenna. And it can go for a very deep penetration. You don't have to take the aircraft to Pakistan to track what is happening in Pakistan. You only have to fly some 250 kilometers inside our border, parallel to the international line. You can know what's happening on that side. In fact, I was also once flying near Jodhpur. We were flying about 150 kilometers parallel to Pakistan border. F-16s taken over from Chitrala. I forgot the name of the air base in Pakistan. We were able to, F-16s were supposed to have low RCS. We were able to pick up about 300 kilometers plus away. Such is the ranges you can get. These numbers you take it with a pinch of salt because ranges are secret numbers. The radar has a surveillance capability over any terrain. We were flying over sea, we were flying over very dense Chabua, like northeast environment. I'll show you some videos there. On Himalayas, which is the most difficult for anyone to, any AWNC is to pick up targets over Himalayas, because the average height at the greater Himalayas is around 6 kilometers and you are flying at 8 kilometers, means you have only a gap of 2 kilometers. The clutter is going to be huge. Ground clutter that is going to come is going to be very huge, such that it can saturate your receiver. So the main thing is how to come out of the saturation, how to track these. Those days we were tracking the Chinese targets. So how to track them still with this sort of environment behind. And we have interleaved for the first time. It was introduced in India indigenously, that you can see air targets and sea targets simultaneously. I'll show you a video. And this is how it works. A normal search, it picks up. Once it picks up, it has to know it is a target, not a false alarm. So it puts one more beam there. We call it as verification or confirmation. Picks it up. There's someone video. That's why it's not here. But then it goes into a loop called track in it, where actually it is a track or a false track is found out. And then if the track is maneuvering, it will go into a full track mode, in the sense that it will update rate is going to increase. The general update rate is, let's say, 10 seconds. It can go to a update rate of 1 second or 1 hertz rate, so that you can track very highly maneuvering targets. I'll show you some such very high G maneuvers. And it can also do sea surface surface search, where we can pick up ships up till the horizon limit. Horizon limit, as I was saying, is going to be around, for 8 kilometers altitude, around 320 kilometers. But you can see much beyond because of the refraction what happens on in the atmosphere. And this is how the search happens. Not necessarily. This is not how it happens, just to depict it. It actually opens like a flower. That means actually it was opening like a flower, because one, we want to do time management. Two, we wanted to fool the EW, that because if it is no longer a constant time, so it will fool it. And now it picks up that the verification is happening, and then it you can see the electronic beam agility. It is going and coming back to any place, any time, that beam. You see, it is not going in any standard way, or it's, you can see that it's picking and then immediately it is searching here or there, or which is not possible with a conventional radar. But to make the radar, we have to have very, very low side lobe levels, because most of the clutter which is coming from the ground actually comes from the side lobes, and they are going to be extremely deleterious to the radar. Now let us suppose 102, I said minus 102 or minus 100, such is the noise level. If the returns coming from are little higher, let's say minus, instead of minus 102, it will go to 5 dB higher, let's say minus 95. You lost huge ranges in the radar. So it cannot go to that extent also. So we have to have very, very low side lobe levels, and minus 110 dBm, two-way side lobe, is what is achieved in the antenna. A very, very low side lobe level. And as I was saying, to counter any one of the jammings, we have a side lobe cancellation. We can do multiple side lobes cancellations at a time. This radar was, in spite of multiple trials from Indian Air Force, they could not jam the radar. Such is the capability of the ECCM of this radar. Okay, some design parameters, I'll skip this. But suffice one point, that when the ground-based radar, all clutter comes with zero Doppler because that is not moving from the radar point of view. So if you filter this out, the entire clutter is gone. And that such a filter is known as a moving target indicator. But if you have a, let it move a little. If you have a airborne radar, the clutter returns are going to come from all the way from plus infinity to minus infinity, or plus infinity is not a good way, plus where you are going to hit the beam maximum to minus where you are going to hit the beam maximum. Someone can guess what would be the place at which what would be the speed of the ground with respect to the aircraft in the front direction. If let's say 100 meters, 200 meters per second is the aircraft velocity, the incoming ground will be at 200 meters per second, and the outgoing ground will be again 200 meters per second. So one is plus, one is minus. So the coverage is from plus 200 to minus 200. Everything is covered by the side lobes of the radar. So you are not left with any space in the frequency domain to pick up the target if you have bad side lobes. And this is how the clutter looks like. Let us suppose that is the noise floor, and you have a target here. Easily you can pick it. Similarly, if you target outside of that platform speed, it is going to compete with noise, you can pick up easily. But if you see, if it is coming in the side lobe clutter here and there, it is impossible to pick it up because it is submerged in the side lobes. And therefore, the design of the antenna is so very critical in airborne radars. And this is the altitude return. This is the one which is used by the radar in the aircraft to actually know how high it is flying. It just picks up this clutter, which is the peakmost point, and try to track that point. And that's how radars are developed. All the aircrafts will have radars. Okay, now a little, the same thing is what is depicted here. So for clutter handling, we have developed many new techniques which are not there in any textbook. So for example, one technique which we called as temporal decorrelation, means in the time they decorrelate, you can see how thick is the clutter. If we do not have such a technique, to how sparse is the clutter after the technique has been applied. And this I have discussed this. It also does classification because there is an IFF. The radar velocity also can be used as classification. And some of the results I'm showing here, that's a Su-30 which is flying another 10 minutes. This is a fighter. We started with on a rooftop. We placed the radar on a rooftop, started tracking. This is a fighter aircraft which is taking about 20-25 high G turns. Every circle is a turn which is, not you in a aircraft, commercial aircraft, you will have a banking angle of how much? 10 degrees. So your turn is very smooth. You will not feel it. If you have a 9G turn, your body weight will be how much? 90, if 10 kg is if you are 100 kgs, let us suppose, for ease of calculation, you are 900 kg, so you cannot lift your hand. So when a pilot actually takes a 9G turn, he cannot lift his hand. Such is, of course, they have huge training to overcome it. But what happens is the blood from the brain goes down and they have blackouts. To overcome the blackouts, they have anti-G suits. If you see the pilot's suit, flying suit, there are anti-G valves connected to it, and they compress at all the other places so that the blood flows into the brain. Otherwise, the pilot will, lose consciousness and the aircraft will not recover. These are all unstable aircraft. For your information, any fighter aircraft, if you look at the control system, they will see to it that a pair of poles are on the imaginary axis. If you have a stable system like our fighter aircraft, if you look at the control system of our commercial aircrafts which we fly, all the poles will be on the left-hand side so that it is a stable flight. Not in the case of a fighter aircraft because it has to take huge maneuvers. They will see to it it is marginally stable, means they'll place two poles because they always come in pairs. You all know that imaginary numbers cannot come otherwise unless you have complex numbers on the trace of the matrix or on the, which is not necessarily the case, and you will end up with a real matrix, real generally positive definite, and there in this aircraft they will make it positive semi-definite. That means at least some of the two of the eigenvalues are zero. That's how the fighter aircrafts are designed. So this is one such fighter. It is a Su-30 for that matter, and this is how the maneuvers happen. Okay, and sorry, can you go back? Here is a helicopter which is taking turn. Helicopter turns are pretty easy to track. Here there are Su-30s. Su-30s, this is a very zoomed figure. Huge maneuver. You will not be able to see because it's too zoomed. What is the radius of the curvature generally? If you have a 9G turn, that means V into omega is 90 of the order. And if you are flying at, let's say, 250 meter per second, omega is of the order of 90 by 250. So you can know how much time it takes to take a 9G turn, maybe 20 seconds to finish one turn at such huge velocities. So you can imagine how, huge is the omega. And that is a huge number of aircrafts, being tracked. This is one of the most difficult targets to track is a ship. Not because the ship is small. It's because the sea gives a lot of clutter. And you have to pick up the target within the clutter. You can see the clutter, but still you can see the target being tracked without any problem. And you also see there are no false tracks coming, zero false tracks in spite of such huge clutter. This we have used, if you the Huff transform you study. So it is a Huff transform based track before detect algorithm. And here one of the greatest difficulties in a radar is to interleave modes. So here we have interleaved two modes, air to air. We were flying along the west coast. There were some aircrafts which were commercial aircrafts, and these are ships which were generally there. So you can see both being tracked simultaneously. There, this is a video. This is an aircraft, and these small things are the ships. And can you press here on this? It's a video. And some snippets I'm showing how this and this are ground based. This is airborne. This is on AWNC. This is also a AWC video. You can see the AWC here and it is here. So this one you can see is a fighter aircraft taking n number of turns, but you get that track ID held from beginning to end as the same number, means we never lost the target at any point of time. Here is, can you press here? There are two targets which are actually closing on to each other, and we have to tell that there are two targets even when they are at the closest, maybe 100 meters, maybe less than 100 meters. Numbers, you take it with a pinch of salt. Now they are going to align to each other. This is from ground, therefore they can do. From air, it is so very difficult to align. I'll show you one such trajectory where in the air they should be in one specific domain, one specific axis. See, they are now aligned, still being tracked as two different targets. You can see the two numbers. Now here you see it's AWNC flying. Can you press this? And they are as close as 100 meters to each other uh, in a formation flying. And we were able to track both of them. If you zoom, you can see actually there are two numbers overlapping on each other. On this side, we went to Gwalior to test the high G turns of aircraft. And this is a very highly maneuverable aircraft. As I was saying, maneuvering is no longer a very necessary requirement from a fighter aircraft because the days of dogfighting are over. You do not come closer than 100 kilometers. If to enemy aircraft is anywhere 100, 150 kilometers away, it's a gone case. Means it will be removed by a beyond visible range missile. And here those small kinks you see, they're actually, now it is taking one 9G turn. Such, it does very fast. You still should be able to track the target continuously, giving a target information which is enough to fire a missile. Next slide. And this is a combat scenario where you have 20s or 30s of so many targets. Actually, there will be five controls flying in the aircraft. In this case, AWNC. And this now we are developing a newer version. Here, because there are 5 people, that 3 of them will be used as radar controllers. So each one will be assigned a particular area. So they will see all the aircraft in that particular area and try to guide the fighter aircraft to intercept them. And that I will show you as a small video. Okay, these are some of the Indian programs that are, in the going on. And at the end, I wanted to show you some, because today I did not want to talk about Uttam. It will take a lot of time. I limit it to primary radar. But today's scenario is this. This is the world's best radar as of now. As of now, it means actually we are designing a much, much better radar than this called Virupaksha. You can see it in the net, Google it. This is APG 81 on F-35. And this is the RB2 on Rafale. This is the Chinese AESA. This is supposed to be the best the radar with the highest range on Raptor F-22 has around 200 kilometer range for a small fighter aircraft. But the one which we are developing for Su-30 has much more range than this. Because it has bigger nose, it has some 1700 TR modules. We have much more than that fitted in a area which is bigger than a Raptor. So Su-30's range therefore is much more than a F-22 range. Anyhow, that is the radar what is there in the fighter aircraft Uttam. Most of you, anyone saw this figure? No. Okay. Anyhow, that is Uttam radar. We showcased it in 2017's Aero India show. We removed the radome, made a glass radome, fitted it on the aircraft just to demonstrate it to the public. Can you press this? I'll just a glimpse I want to show on. You can remove the sound. First, you cut off the sound. You can removed. You can play the first video. We made a small video on how we went about developing AWNC, primary radar for AWNC, not AWNC. You can press on this. This program actually was started as ASWAC on a British aircraft. hacker aircraft. HS, I forgot the number, but that met with an accident, and scientists from DRDO, many of them have passed away in that accident. But this is the second version. It's on an Embraer 145 aircraft. Embraer 145 is a executive jet. And this all I have told you. It has multiple sensors and all the necessary links to communicate. It has ESM, ELINS, comment, it has IFF, it has radar, it has new one has including IRST, not this one. But IRST is mainly are for fighter aircraft, not for early warning systems like this. Okay, this is a Embraer 145 executive jet on which the antenna is integrated, LON and the different subsystems. Okay. So we went on an incremental approach. We made the L star, which I was talking about a little earlier, to start with. First to start with a small radar, then a big radar. Then we went on to integrate it as a rooftop radar. Then we started flying in 2013. And 2014, we completed all the necessary development. 2017, it was inducted into the Air Force. And the different phases of our development, ground testing, and so on. And this is the rig in which we did the testing with the AAAU on rooftop and all the other electronics here. And this is the target which I was talking about, a very high maneuver. And we have flown in all sorts of terrains, as I was saying. Sea, then desert, huge foliage, and on the Himalayas. Everywhere we have flown to show that AWNC can work against any terrain type, because terrain becomes important when, especially if you are competing with clutter. So in Rajasthan also we have flown. Okay. Many places. And okay, this is a huge number of targets being tracked simultaneously. It's called large force engagement. Number of targets, more than 20 fighter aircrafts flying, and we were able to track all of them. And it was again used in all our Republic Day parades. You can see them as we move forward. This, I think, is a exercise that is happening. Not very sure. And this is a Republic Day fly past. You can see so many targets flying and the radar tracking all of them. This, I don't know what there is there. Su-30, okay, Su-30 formation it seems. And then we have evaluation against Su-30s in dense foliage. And the Iron Fist we have participated where multiple fighter aircrafts were flying in Rajasthan. Every year this happened in Rajasthan to showcase India's Air Force powers. These are commercial aircrafts. You can see they are going in straight lines. These are fighter aircrafts. Okay, many breakthroughs we had because we did not have anything to start with strictly. No AESA, no understanding of clutter, no prior experience in how to compensate motion. And next, can you come out? A glimpse of, because of the paucity of time, I'll just escape, close it. Come there, go to the presentation mode. And the second one, I'll just, we made a small video on how we developed Uttam. Can you go there? Press the second one. No, second. So that's the, in fact, there is a book called Flow. If you would have read it, it says the journey is much more satisfying than the result. So that's why it is journey. And there is one novel by Somerset Maugham. He says, bitter is the end that is achieved. The end which is not achieved is also bitter. The end which is achieved is also bitter. So all ends are bitter. Only the journey is satisfying, and that is the journey. This is first we started as a mechanical. This is what I was saying. It's a mechanical radar. It's not AESA radar. So then we went to a prototype AESA radar on rooftop. Then we integrated it on a executive jet Hawker 800. For the first time, we did such a feat in India, because to qualify an aircraft to fly is no joke. Once you cut open a nose and integrate a radar, I will show you how it happened. And we developed all the necessary modes on and tested on Hawker before we went to the LCA, because LCA 1 hour of flying is about 70-80 lakhs. Here 1 hour of flying will be 10 lakhs. So that is the sort of difference. The most we will try it out on a commercial aircraft before we go to fighter aircrafts. In fact, any country does that. I went to France as that Rafale. When we purchased Rafale, there was a committee formed for radar. I was there. So when we went there, they also have a beautiful flying test platform, which they use to test the RBUT, which is on coming back. This is the head, this is how the integration on the commercial aircraft was done. This is a Hawker 800 aircraft. And the assembly happening. We opened everything on inside the aircraft, and then did all the aerodynamics and thermal for the aircraft to see that the aircraft is fit for flying with these modifications. And this is how it was. This is what is cut open. There was a weather radar here, which was open, and we fitted the LCS nose portion, because it should look like LCA. This is the front end of station 1 of LCA. And that was the pilot. This is the radome. And it is cleared by Semilac to fly. This a great moment, because it's almost so very difficult to get a clearance for flying, and this is the first flight happening. This is a HAL airport in Bangalore. We called it Virupaksha, this aircraft. You can Google it. And the same name we gave it to Su-30's midlife upgrade radar also. Virupaksha, because, this, can you stop here once? This one is 2 fighter aircrafts doing scissors maneuver. The man who commanded the Air Force during the 4 days of Op Sindur is one by the name Air Marshal Misraji. So he was at the time commandant of ASTE. ASTE is our aircraft test center, Air Forces. So he said, no, don't track single targets. You track 2 targets which are doing a scissors maneuver. They are going like this, and you have to continuously track them as 2 targets. So we were able to track them about a dozen times as 2 targets. So incidentally, he was later in Op Sindur. Okay. So different modes, you can see the silhouette of the ship. This is known as ISAR. ISAR images. Very, very, any pilot who has seen it multiple times can easily recognize. These are clouds. Okay, this is the team, and that's the aircraft what is. Then on LCA we integrated. This is being integrated on LCA. This is a LCA aircraft. And okay, the achievements thereof. We were able to track targets. This is the some indicative range for this aircraft. It'll be more than that. And then this is called raid assessment. In raid, you have multiple aircrafts coming together. They're very close by, but they are picked up as two targets still. It's called resolution in range. Now you can see this aircraft is doing a huge role. You would have seen that moving a lot, the role of the aircraft. And in spite of that, we were able to hold on to the target. And here he is doing a slow roll, and it will go out of the coverage, gone out of the cover. This is called close combat mode. This square is where you can see a black dot, if you see closely, is a fighter aircraft about a kilometer away or a couple of kilometers away. We should lock on and the square should not move. If the square is tightly locked on, they can release a weapon, close combat weapon. And this is a real beam mapping where we put the beam and know any disturbance in the reflectivity coefficient. So there you can see that that's a lake, water body, and water bodies generally have very low reflectivity coefficient for RF. So you will get a black image. You can know that this is water. Okay. This is a Doppler beam sharpening. This method is known as Doppler beam sharpening. It's a first version of SAR, but used to, as an indicative method because it has a huge swath, the range which covers at any given point of time. Then this is a high resolution image. Because of the light you cannot see, but you can see this black portion is the tarmac. No, not the tarmac, the what do you call it, where the aircraft take off, runway. And this is called GMTT. I was telling from 100 kilometers away, you are able to put the target within 30 meters. That is 0.02 degrees. You can see it moving along. And this is when you want to bomb a ground point, you have to know it very, very accurately. That's called, this is a mode which gives huge accuracy ground points. This is the weather mode. You can see the content of water in the weather. If it is red color, it means that it has more water content. And this is a navigation mode. The aircraft can then go like that, away from the clouds. And then I think the next one is, this is a little slow. This is you have a mountain in front. Immediately we can know that there is a mountain in front. You have to take a upward movement. And that is how actually the SAR image looks like if the light is proper. And you have multiple points like they are aircraft. These are the aircrafts which are parked. Okay, that's it. Can you close this? Oh, wait. This is the aerostat which I was telling. It has a gondola, and in that gondola there will be a radar, and it flies at around 4.5 kilometer altitude. So that this is not this small. The one which radar will be around 70 plus meters long and has 24,000 cubic meters of helium. Next, you can close this. Then we thought I will make a video because you wanted a popular lecture. So I made a small AI video with how actually warfare happens today. A small video. Okay. You can put the waves on. Let us suppose there is from a hostile air base, some JF-17, these are Chinese models of Pakistani aircraft, JF-17, they have taken, they're taken off. Now there is a AWNC flying somewhere here and it picks up these targets. Okay, it is radiating and picks up those targets There is a little mistake in this, and it comes to a control. I was telling CCS. It comes to a hub where all these are known immediately. What are the aircrafts flying at the central point of the Air Force? It then sends that information to a fighter aircraft. Here it is depicted as LCA. The pilot then, uses the radar. This is the Uttam radar, and picks up the 3 targets. Is radiating and picks up. This is just a depiction. Picks up those 3 targets and releases 3 beyond visible range missiles to each one of them. And these are Astra, our own missile. And they have our own seeker. Seeker is the one which does the end game. It is a small radar in the nose of the missile. As it comes, this seeker takes over when it is in the end game. There it is locked on. And when it comes close, there is a radio proximity fuse here, which knows it has come very close and explodes and takes off the aircraft. This is how the network warfare happens today. Someone is speaking, someone is telling someone else that someone is probably he is using his own weapon or someone else's weapon. Anything, it is no longer a single aircraft going and flying. It is the entire system which is giving you the ability to, do such interception. This is no longer some sort of, is not a science fiction. It is what happens. Okay, next slide. So that's about a little about the Indian airborne radars and warfare. Jai Hind, Jai Bharat. Any questions? Sir.
Not only the battle, but development is also a big team game. How does this coordination and things happen? Because there are many specialists who have to come together.
You are correct, sir, in the sense that when we develop, we have a Air Force team continuously attached. See the screens, what you are seeing, they have to be used by the pilot. And the pilot only knows how to place the screen, different elements on the screen. Without the pilot, therefore, you cannot develop. So pilot is an integral part of the development. Then if you have a AWNC, you have flight controllers. They are the one who are using so they are the people who will be sitting along with us during the development, telling what they want. So the user is always an integral part. This is one side. Second side, we have academia. There will be at least, I didn't bring out, more than a dozen institutes and universities which have worked with us to make this happen. And there is a foreign collaboration. We had a Airbus consultant to tell whether our design is right or wrong. He will not tell what is the right design. He only will go through the documents and tell whether we are going in the right direction or not. Then we have our own industry. The entire ecosystem of the industry has been used. More than 100, 150 industries have been involved in making this to, bring it to this shape. Whom am I forgetting? You have academia, you have user, you have industry, you have collaborators, and you have multiple of laboratories, not just of DRDO. We also take help of CSIR as well as sometimes ISRO. Most of the times CSIR. What I have shown you as the aircraft certification has happened with the help of NAL, which is in Bangalore. So then we have certifying agencies apart from these, who are the actual people who will tell this aircraft can fly or cannot fly. For example, we have a certifying agency called CEMILAC within the DRDO laboratory system. But we also have within the Air Force an organization called DGAQA, which will have to clear the aircraft for every flight. So I don't know how. These are the breadth of people who will be involved when you are actually flying. And we have also private parties which give us aircrafts, which help us in flying. They supply us pilots. AST, most of the times, if it is AWNC, it was flown by AST pilots. And LCA was flown by NFTC, National Flight Test Center pilots. And that other Hawker 800 I have shown was flown by private pilots. So you have, even for flying, multiple people who are involved. So I'm suffice to say that it is not an individual effort. It's an effort of maybe a few hundreds of people or even more. And the sort of revenue that it generates, Uttam development alone has it has a capability of 50,000 crores. Now I'm not talking about the AWNC. AWNC, because of the success of Mark 1, we have Mark 1A, Mark 2, which are now running projects. And on Uttam, we have LCA Mark 1A, LCA Mark 2, AMCA, twin engine deck based aircraft, that is for the ships. These are the 4 LCA variants, but bulk are going on Su-30 midlife upgrade. So we have a huge number of different types of aircrafts on which Uttam is, going in one way or the other. So overall, it is a huge industrial base actually, which is helping in productionizing.
My question. The drones are coming. I think that this radar has got a cross-sectional area. Well, how you are countering the attack from drones and to detect the drone?
Okay, sir. We have a D4 system developed by us. Drone detection and destroy. So when a drone comes, the main thing what drone has is it has an RCS of minus 30 dB meter square. That is about 0.001 meter square RCS. That's small. So to pick it up is therefore that much difficult. But generally we can pick up at about 8 to 10 kilometers now. For the drone to move 8 to 10 kilometers takes a large amount of time because they move it at about 10 meters per second or so. So it is therefore feasible to count. And I told also we have an electromagnetic pulse and a laser weapon to destroy them while they are flying. And these have ranges in excess of 2-3 kilometers. So you can destroy drones up till 2-3 kilometers and detect them at about 10 kilometers. But the main thing, that is the question what you wanted to ask. However, the main problems in drone detection are, if you have a bird, you have a flock of birds, how to distinguish this flock of birds from the drone? That's a big problem. Or if you have a ground clutter, which is going to compete with the drone and the drone is moving at very low speeds, how do you remove the clutter and pick up the drone? That is a big problem. So these are the problems that generally are encountered by drone detection. If you have UAVs, on the other hand, this is about drone or those copter types. UAVs are like aircraft. They fly at, let's say, 25,000 feet. They can loiter like a predator drone. That is a UAV. That can launch weapons. Predator drone can launch weapons. They can be picked up at around 100-200 kilometers without any problem. It is like any other aircraft. The main problem is this small copter driven drones, which are more difficult to pick up and destroy. And that we have ranges up till 10 plus today. If that is not the question. But you have no other way. The warfare is changing. That's called a low intensity conflict. Or we have two divisions which are handling this in DRDO. This is one, which does the low intensity conflict types, which again drone is a part of that, where we try to some sort of, in fact, even in NPOL, we have a project where we can pick up drones up till some range, which we are doubling today. Hopefully, we'll be able to do even with sound. So whatever sound I was telling about in the beginning is coming back in some other way. And whatever I told, they thought that the EM pulse they can inject and kill. Let's say that video has a sheep, but today you can use it to kill a drone, a EM pulse at around 2 kilometers range. You have you send a electromagnetic wave, huge power, and then kill them. It's demonstrated already. Sir. Be used in the warfare mode. It is better accuracy with the Sir, there are two parts to it. I will answer it from a laser point of view. LIDAR will come to. Lasers today I have shown you are weapons. They are using it as short range weapons. Lasers are also used for ranging. We have a laser pods for ranging on all our fighter aircrafts. They are used for ranging. And today at NPOL we are using LIDARs for submarine detection. They can be detected at around, let's say, as of now, about some tens of meters depth. So probably tomorrow they will maybe increase, but LIDARs are used in different ways. Madam. Thank you. Radar is at the heart. Madam, I have been working radar for 2 decades plus, but I don't know Kannada as much I don't know Malayalam. The sonar is more challenging. Not from the point of view of the algorithm, but the point of view of the medium. Because we cannot see the radar easily thousands of kilometers, 10,000, no problem. You only have to have a big aperture. Sonars, very, very difficult because submarines, the medium is bad to detect a submarine, not the sonar. So, therefore, it is sonar which is more challenging. But, madam, I have hands on radars. I'm only a manager in sonar. There is a fundamental difference.
I have doubts.
Now, seeker has been indigenized. So, there are two types, two modes in the seeker. One is called the monopulse mode, and the other one is called the imaging mode. As far as I know, the monopulse mode has been perfected. The imaging mode, I do not know. And when are they going to replace? I'm not sure because that's more a managerial decision than a technical decision. Sometimes it is more managerial than technical.
Excuse me, sir. Sir, I just want to ask, sir, you in the beginning you told about IFF, identification front and fore. So how can you say that an aircraft is a front and the other is a fore?
I will tell you, you give a secret code. You today, secret code, all of the pilots you use, the IFF will be coded with some, how are you, let's say, or some number. So when you interrogate it, you interrogate with this number. So if it is an enemy aircraft, it doesn't know.
Okay, sir, okay.
But our aircrafts will know that I have to respond. So they respond back. So once you respond back, okay, in fighter aircraft, I have not shown you the full thing. The fighter aircraft also has on top of it IFF elements, which I have not shown. So once the enemy aircraft is picked, the IFF sends a signal to it. Are you enemy or a friend? If it is not responding, it will be assumed as an enemy and it will be shot down. Sometimes it happens that we shoot our own. It happens sometimes. Thank you once again.
Thank you very much, sir, for that insightful lecture. Your valuable perspectives on sensors for airborne warfare have truly enriched us and provided a deep understanding of this important field. Thank you, sir. As a token of our appreciation and gratitude, may I request Professor P.R.S. Pillai to kindly present the memento to Dr. Duvvuru Seshagiri. As we come towards the conclusion of this memorable and enriching program, it is time to express our gratitude to all who made this event possible. May I now invite Dr. M. Gopalakrishnan Pillai, Director, STIC, to propose the vote of thanks.
Respected dignitaries, faculties, students, ladies and gentlemen, today's program marks the second memorial lecture in the series instituted to honor the legacy of Professor K.G.Nair, the visionary academician who dedicated his life to science education. This memorable lecture series is being organized by the Department of Electronics, CUSAT, where Professor Nair served as the HOD of the department for many years, along with the joint efforts of STIC and CSIS, the two organizations established by him. Last year, we inaugurated the lecture of the series was held at CSIS, and this year we are grateful to the Department of Electronics, CUSAT, for hosting the memorial lecture as part of its Golden Jubilee celebration. At the outset, I sincerely thank Dr. Deepthi Daskrishna, Professor and Head of Department of Electronics, for graciously hosting this program and for working tirelessly to ensure its smooth and professional conduct. Thank you, Madam, for your sincere and dedicated efforts. I express my heartfelt gratitude to Professor Arun A.U., Registrar CUSAT, for presiding over this function. Despite his busy schedules, he kindly consented to grace this occasion. We are truly thankful for his support. The relevance and importance of warfare system in today's global scenario is well known to all of us. The technological capabilities of Indian defense systems, particularly in electronics, sensing technologies, and artificial intelligence, have been demonstrated convincingly in the recent past by our defense forces. In this context, we are honored to have with us Dr. Duvvuru Seshagiri, who is spearheading one of the prominent research center of DRDO, the NPOL. He has clearly explained the critical role of sensors in airborne warfare and enriched all of us with his valuable insights. On behalf of the organizing committee and on my own behalf, I express our deep sense of gratitude to him, and I request the audience to join me in giving him a big round of applause. We are honored by the presence of Professor Babu Joseph Sir, former Vice Chancellor CUSAT, who was a contemporary of Professor K.G.Nair and worked closely with him for many years. Thank you, sir, for your kind presence and sharing his valuable memories and reflections in this forum. I also express my heartfelt gratitude to Professor K. Shivaprasad, Professor, Department of Ship Technology, CUSAT, and former VC KTU. Sir has been playing an active role during the planning phase of this program. Thank you, sir, for your guidance and delivering the felicitation. We are also pleased to have with us Mr. Rajan Tuwara, the eminent writer representing Professor K.G.Nair family. On behalf of organizing committee and my own behalf, I thank him for being here today and delivering the felicitation. A special mention and a heartfelt thanks goes to the entire family of Professor K.G. Nair, especially his sons, Dr. Gopalakrishnan and Dr. Balakrishnan Nair, who are watching this event online from USA. Your unwavering moral and financial support and your continued engagements have played a crucial role in making this event possible. Professor Nair's legacy lives on through your efforts, and we are truly grateful for your contribution to this important occasion. I thank all the dignitaries, guests, faculty members, and students for your presence here today. Finally, I place on record my appreciation for the staff and students of the Department of Electronics, along with the staff members from STIC and CSIS for their dedicated efforts behind the scene. Once again, thank you all for being part of this memorable occasion. Thank you and have a wonderful day ahead.
Thank you, sir. With this, we come to the end of the Professor K.G.Nair Memorial Lecture 2026. On behalf of the organizers, I extend our sincere thanks to our distinguished speakers, respected dignitaries, and all participants for your gracious presence and valuable contributions. The invaluable contributions and enduring legacy of Professor K.G. Nair continue to inspire generations with deep respect and admiration. Thank you all for being part of this solemn and meaningful occasion. Have a wonderful day ahead. Tea and refreshments are arranged in the dining area. Thank you.